Before we start, a quick thank you for being here. If you enjoy slow, detailed journeys through Earth's history, feel free to support this channel by leaving a like, subscribing, and sharing this video with someone who might find it relaxing or interesting. It really helps this project continue. I'm also curious about you. What time of day are you listening, and where in the world are you watching from? Let me know in the comments below. Now let's go back to the age of Pangea. In deep geological time, long before familiar continents stand in their current places, Earth turns beneath a sky and over an ocean that already covers most of its surface, but its land is scattered. Pieces that will one day be known as North America, Europe, Asia, Africa, South America, Australia, and Antarctica sit far apart, drifting slowly on the outer rocky shell of the planet. This slow drift, measured over tens of millions of years, brings them together until they join into one broad landmass. A scientist in the early 20th century, Alfred Wegener, notices that the outline of eastern South America matches the curve of western Africa, and suggests that the continents were once joined. Modern plate reconstructions test and refine this idea, and now show how a single supercontinent called Pangea comes together and changes Earth's global geometry during the late Paleozoic and early Mesozoic eras. A supercontinent is a large cluster of nearly all the major continental pieces joined into one connected body. When Pangea exists, most of Earth's land is gathered into this one unit, wrapped by a global ocean that stretches almost unbroken around it. The time window for Pangea's full assembly falls roughly between the late Carboniferous and early Permian periods. In this interval, several older continents and microcontinents collide weld and lose their separate coastlines. To the north, regions that will later form parts of North America, Greenland, and northern Europe link together. To the south, the older supercontinent Gondwana already holds what will become South America. Africa, Antarctica, Australia, and the Indian subcontinent as a single mass. Over many tens of millions of years, the northern and southern clusters converge. The collision zone between them grows into a wide band of deformation and uplift, and the line where they meet becomes a major backbone through the future supercontinent. By the time Pangea stands as a joined landmass, this line runs from regions that will become eastern North America, through what will one day be northwestern Africa, and onward through future southern Europe and beyond. Seen as a whole from space in this interval, Earth shows a striking pattern. One side of the globe is dominated by Pangea, a single irregular mass that stretches from high southern latitudes to high northern latitudes. The opposite side is almost entirely ocean. The supercontinent is not a simple shape. It shows long embayments and peninsulas, rounded bulges, and narrow extensions, but it remains continuous across many thousands of kilometers. A broad northern region, often called Laurasia in reconstructions, holds what will become North America and Eurasia. A broad southern region, often called Gondwana, holds the later fragments of South America, Africa, India, Antarctica, and Australia. Between these regions, suture zones mark where older oceans have closed. The outlines of the future Atlantic and Indian Oceans do not yet exist. Instead, the outer coastline of Pangea faces a vast surrounding body of water known as the Panthalassa Ocean, which means all sea. Almost everywhere along the outer edge of the supercontinent, any direction one travels away from land eventually leads across Panthalassa. Along one long curving margin of Pangea, however, the arrangement of land and sea is more complex. Here, between the northern and southern segments of the supercontinent, stretches a belt of interior and marginal seas, known in later study as the Tethys region. This is not yet the narrow ocean that will eventually open between Africa, India, and Eurasia in later times, but rather a set of connected basins and embayments that occupy a zone along the equatorial to low latitudes. Small continental blocks and island arcs may stand within these waters, forming partial barriers and shallow platforms. These features give this side of Pangea a step transition from interior land to deep ocean. In contrast, many other parts of the margin pass more directly from continental shelves into the open waters of Panthalassa. Because the supercontinent spans so many latitudes, its overall geometry creates a continuous land bridge from near the South Pole to regions close to the North Pole. In the late Paleozoic parts of what will become eastern North America and northwestern Africa lie relatively close to the equator, while the southern parts of Gondwana extend into high southern latitudes. Over time, as plates continue to move, the entire configuration drifts somewhat northward, but during the core Pangea interval, the supercontinent still covers a very wide band of latitude. This arrangement means that coastlines exist in both warm equatorial zones and cooler temperate zones, with some sectors approaching polar regions. The mass of land is large enough that its central interior lies far from any sea, while its margins remain narrow fringes where land meets water. The geometry of Pangea at the planetary scale also includes long mountain belts and highlands that trace the scars of earlier collisions. These belts, which will later be partly preserved as the Appalachian Mountains in eastern North America, the Atlas region in northwestern Africa, and the highlands of parts of western and northern Europe, now form a nearly continuous line that runs through the interior of the supercontinent. At the level of global outlines, this high-folded zone is a subtle swell along the joined margins of the older continents that have collided. Other highlands, such as ancient shields and plateaus in what will become parts of Brazil, South Africa, India, and Australia, stand as relatively stable cores within the southern part of the supercontinent. They help define the overall shape and thickness of Pangea's crust, but on a global map appear mainly as broad, slightly elevated blocks within the landmass. Even while Pangea exists as a single unit, its shape is not fixed. The same plate motions that assembled it continue to act so that small adjustments in outline take place through time. Narrow rift valleys begin to open in some regions as the lithosphere, the rigid outer shell of Earth, stretches in response to forces at its edges and base. The future Central Atlantic region, for example, is marked by zones of extension that will much later grow into a full ocean basin. In the Pangea interval, these early rifts remain mostly as linear depressions and local basins, and the overall continuity of the supercontinent is preserved. Far from the continent, ocean floor sinks along long, deep trenches, and this slow recycling of the seafloor over tens of millions of years helps shift the position of Pangea little by little across the globe. Thus, on the scale of very long time spans, Pangea both persists and very slowly changes its global position and curvature, remaining the dominant landmass on Earth, while subtle shifts smooth or accentuate parts of its coastline. Taken together, these features define what it means in physical terms for Earth to host Pangea. Almost all major continental crust is gathered into one irregular block fringed in places by microcontinents, and interior seas bounded mostly by a single vast ocean and crossed by long-heeled suture zones and highlands. The planet's surface, when mapped at this time, shows a strong asymmetry between land and sea from one hemisphere to the other. This global geometry is the basic arrangement of land and ocean on Earth during the time when Pangea exists. When Pangea stands as a joined landmass, its shape is complex, but can be described in broad connected pieces that are now well constrained by plate reconstructions and by the record stored in rocks and fossils. The supercontinent occupies one side of the planet as a single, continuous body of thick continental crust. But that body is not a simple circle or oval. It stretches as a long, uneven band from high southern latitudes to high northern latitudes with a slightly skewed position relative to the equator. In many reconstructions, a large part of its central belt lies near low latitudes, while broad arms of land extend both toward the south and toward the north. The outer margin of Pangea is a continuous but irregular coastline marked by wide arcs, narrow peninsulas, and embayments that cut deeply into the continent. Some segments of this coastline face directly onto the largest ocean on Earth, at this time the Panthalassa Ocean. Panthalassa is the global ocean that covers almost the entire opposite hemisphere from Pangea. Its floor is made of oceanic crust that spreads from long mid-ocean ridges and sinks at subduction zones, but on the surface it appears as a broad expanse of water that wraps around the supercontinent. In every direction away from the outer margin of Pangea, except where interior seas intervene, the open waters of Panthalassa eventually stretch for many thousands of kilometers before reaching any other land. Along much of this contact, the transition from continent to deep ocean passes through a typical sequence of continental shelf slope and abyssal plain. The continental shelf is the shallow submerged fringe of the continent where thick, buoyant crust allows the sea floor to lie at relatively small water depths. This shelf can be wide or narrow, depending on local tectonic history and sediment supply. At the edge of the shelf, the slope descends more steeply toward the deep ocean basin, where the floor of Panthalassa lies at greater depths. Around Pangea, the width of the shelves varies. In some sectors, especially where stable continental interiors meet the sea without recent major deformation, the shelves may be broad and low with gentle gradients. In other sectors, where older collisions and crustal thickening have created steep coastal ranges, or where the continent is being stretched, the shelves may be narrower and more irregular. Outboard of these margins, the oceanic crust of Panthalassa carries long volcanic ridges and deep trenches. But from the point of view of the global geometry, the key feature is that this ocean occupies almost all of the surface not taken up by Pangea and a few smaller continental blocks. One margin of Pangea differs from the rest. Between the main northern and southern parts of the supercontinent lies a set of interior and marginal seas that later science groups under the term tethys. The word tethys is used for a broad region of oceanic and marginal waters that occupy a long east-west oriented belt at low to middle latitudes on this side of Pangea. In the interval when Pangea exists, this tethys region is not a single narrow ocean, but a complex zone of basin shelves and island arcs. Pieces of continental crust, sometimes called microcontinents, stand in these waters as smaller land masses detached from the main supercontinent or in the process of moving toward or away from it. Their positions and shapes change gradually, but at any given time they act as partial barriers that divide the Tethys waters into subbasins. These basins can be connected by straits and shallow sills, allowing water to move between them and out into Panthalassa. But they are more enclosed than the open ocean that surrounds the rest of Pangea. The geometry of this side of the supercontinent thus shows a stepped arrangement. Interior, continental lowlands and highlands pass outward into shallow interior seas, then into deeper marginal basins of the Tethys region, and finally into the open waters of Panthalassa. At the largest scale, the supercontinent can be described as having a northern and a southern lobe. The northern lobe includes crust that will later form much of North America, Europe, and Asia. It reaches from low latitudes through mid-latitudes and into higher northern latitudes. Its margins include both nearly straight segments and more indented embayments. The southern lobe is built on the older Gondwana assembly, which holds what will become South America, Africa, India, Antarctica, and Australia. This southern mass extends from low latitudes into high southern latitudes and shows a long, sweeping outline along Panthalassa, with several projections of land and curved coasts. The line where these lobes meet marks earlier collisions that have closed older oceans. At a global view, the contact between Pangea and Panthalassa is strongly asymmetric. On the side that faces Panthalassa directly, the coastline is long and relatively open, and behind it lies the full breadth of the continental interior. On the side that faces the Tethys region, the coastline is broken into segments by interior seas and microcontinents, and behind it lies a narrower region of continental crust before the land transitions to the main interior. This asymmetry helps define broad hemispheres of Earth during the Pangea interval. One hemisphere is land-dominated with the supercontinent, covering a large fraction of the surface. The other hemisphere is water-dominated with Panthalassa, covering most of the area and only scattered small islands or microcontinents interrupting the surface. Although the exact positions of the poles and equator relative to Pangea shift slowly as the lithosphere and mantle interact, reconstructions show that the supercontinent's equatorial zone runs across its central part. This means that the global outline includes equatorial coasts, mid-latitude coasts, and high-latitude coasts, all on a single continuous landmass. In high southern latitudes, the outer margin of Gondwana meets Panthalassa along coasts that are positioned closer to the South Pole. In high northern latitudes, parts of the northern lobe approach the North Pole, though the exact positions at different times within the Pangea interval vary. This continuous spread of land across latitudes produces a global map, where a person tracing a path on the surface from far south to far north can remain on continental crust the entire way, crossing mountain belts, lowlands, and interior basins without ever stepping into the ocean. Within the interior of Pangea, the geometry includes not only highlands and lowlands, but also enclosed or partly enclosed basins that lie below sea level, yet are isolated from the open ocean. In some of these basins, shallow inland seas can occupy low points fed by connections to marginal seas or by river input from the surrounding land. In other periods or regions, these basins may be dry or filled with lakes and river systems rather than marine waters. Their presence reflects the way earlier collisions and crustal deformations have thickened and warped the continental crust. Even in these more detailed features, the outline of Pangea remains continuous across long distances. There are no wide oceanic gaps splitting the supercontinent into separate major land masses. Instead, narrow seaways or rift systems where they exist mostly remain within the bounds of the continental crust, forming elongated depressions rather than full oceans. In certain regions, for example, in the zone that will later become the Central Atlantic, these rifts begin to define linear features that parallel parts of the future coastline. But during the main Pangea interval, they have not yet grown into broad ocean basins. The supercontinent's geometry is therefore both stable and slowly changing stable in the sense that a single continental body dominates one side of the planet for many tens of millions of years, and slowly changing in the sense that its detailed edges, internal basins, and marginal seas adjust under ongoing plate motions and deformation. From the perspective of global geometry, the presence of Pangea means that Earth's surface is partitioned into one supercontinental block and one great surrounding ocean with an internal tethys complex and a modest number of smaller continental fragments. This arrangement, defined by coastline shelf breaks, basin outlines, and the positions of microcontinents, is the physical framework of land and ocean during the time when Pangea exists and remains joined. As Pangea exists through late Paleozoic and early Mesozoic time, its outline is not frozen. The same plate motions that bring the continental blocks together continue to act, so the supercontinent both persists as a single landmass and slowly shifts its position and shape on the surface of the planet. Reconstructions based on paleomagnetism fossil distributions, rock units, and structural patterns show that the main assembly of Pangea is largely complete by late Carboniferous to early Permian time. At that stage, the collision between the northern land cluster and Gondwana has closed older ocean basins and created long belts of mountains and deformed crust along the weld zones. From that point onward, the story is one of gradual adjustment and eventual disruption. In the earlier part of this interval, Pangea drifts as a single unit with respect to Earth's spin axis. Paleomagnetic measurements taken from rocks that cooled and locked in the direction of the magnetic field at the time of their formation indicate that the whole supercontinent shifts somewhat northward during Permian and Triassic time. This motion changes which parts of Pangea lie in equatorial mid-latitude and higher latitude belts. Regions that begin closer to the South Pole move into cooler temperate latitudes, and regions that lie near the equator remain within low latitudes but may rotate slightly. The result is that coastlines and interior areas experience different average solar angles and day-length cycles through the life of the supercontinent, even though the land remains connected as one mass. At the scale of the global outline, these changes appear as a slow reorientation and translation of Pangea across the surface of the globe rather than a major rearrangement of its basic shape. Within the interior of the supercontinent, however, the crust responds to forces transmitted from its edges and from the convecting mantle beneath. As oceanic plates sink back into the mantle around parts of the Panthalassa margin, they pull on the edges of the continental plate. In other regions, upwelling of warmer mantle material exerts push or uplift. Over tens of millions of years, these forces create zones of compression extension and shear within the continental crust. In many places, earlier collision zones continue to uplift and erode, but in some areas, the crust begins to stretch and thin. The most important of these extensional zones for Pangea's outline lie along future breaklines between the continents that will later become separate. From a present-day perspective, the central North Atlantic region offers a clear example. During the time when Pangea is still joined, this region is not yet an ocean, but starts to show a belt of rift basins. These basins form where the crust is pulled apart slightly, creating narrow troughs bounded by normal faults. Sediments and sometimes volcanic rocks fill these depressions. On a map of Pangea at that time, these rift systems appear as elongated, roughly parallel structures that run inland behind the coastal region of what will much later become eastern North America and northwestern Africa. They do not yet split the supercontinent, but they mark lines of weakness along which later breakup will advance. Similar early rift systems appear in other regions, including parts of what will become eastern South America and southwestern Africa, and in sectors of Gondwana that will eventually separate into India, Antarctica, and Australia. Again, in the Pangea interval, these are not full oceanic gaps. They are continental rift zones where crustal thinning, local subsidence, and volcanic activity begin to alter the topography and to modify local coastlines as small embayments and shallow interior seas develop. The Tethys region also changes during the life of Pangea. Early on, the Tethys is expressed as an interior to marginal seaway system between northern and southern parts of the supercontinent. As time passes, parts of the northern margin of Gondwana begin to move relative to the northern lobe of Pangea. Small continental blocks may detach from Gondwana and travel into the Tethys, becoming microcontinents or island arcs. This process widens some segments of the Tethys region and creates new basins between the main continental masses and these smaller blocks. From the perspective of the supercontinent's outline, the Tethys side becomes more irregular. New embayments and seaways appear as these blocks move, and the simple line between land and ocean becomes a nested pattern of land, shallow seas, and deeper basins. Some parts of the Tethys margin experience shortening and uplift, where small ocean basins close, while other parts experience extension, where new basins begin to open. The result is a gradual but significant evolution in the geometry of this side of Pangea, even as the overall supercontinent remains in place. Along the outer margins facing Panthalassa, subduction zones and associated volcanic arcs migrate and reorganize over time. Where oceanic crust is consumed beneath the supercontinent, the position of the trench and the shape of the accretionary prism at the edge of the continent can change. Sediments scraped off the subducting plate accumulate at the margin, adding material and sometimes broadening parts of the shelf and slope. In other regions, the edge of the continent may experience erosion and undercutting. These processes adjust the detailed outline of Pangea's coastal zones over millions of years. While the overall contact between supercontinent and surrounding ocean remains a single continuous margin, the fine scale pattern of headlands, embayments, and shallow platforms is dynamic. Another slow change in the outline of Pangea involves vertical motion of the continent's interior and margins. Thermal subsidence occurs where once thickened crust cools and contracts after earlier orogenic events. Uplift occurs where heat input or mantle upwelling raises regions of the lithosphere. These vertical shifts can convert coastal plains into shallow seas and later back into land, or can expose former shelves as dry areas. Inland basins may deepen link with marginal seas, or become isolated as lakes. Such changes do not break the supercontinent apart, but they alter the distribution of coastlines and interior water bodies. On paleogeographic maps for different times within the Pangea interval, this is seen as a shifting pattern of epicontinental seas that flood low-lying regions and then retreat, leaving behind sedimentary records of marine incursions. All of these processes together mean that there is no single map that captures Pangea at all times. Instead, there is a sequence of maps, each one valid for a certain time slice, that shows a supercontinent with a recognizably similar overall shape, but with different details in coastlines, interior seas, and marginal basins. Early in the history of Pangea, the supercontinent may extend farther into high southern latitudes and carry broader regions of glaciated or cool climate terrains there, while later time slices show the whole mass shifted somewhat northward under a warmer global climate state. Early maps may show narrower Tethys basins and more continuous connections between northern and southern parts of the continent, while later maps show more open Tethys waters and more pronounced separation between the northern and southern lobes. The long mountain belts that mark sutures between the older continents also evolve, with continued uplift and erosion reshaping their topography and influencing how they appear as features in the continental outline. As the early stages of breakup begin, the geometry of Pangea shows the first clear signs that the supercontinent's integrity will not last. Rift systems deepen and lengthen, volcanic activity becomes more widespread along some margins, and new passive margins begin to form where extension has progressed far enough to generate new oceanic crust. Even at this stage, for a time, Pangea still functions as a largely joined landmass in global terms, with only narrow seaways intruding between its parts. However, the coastlines in these areas are no longer simple linear edges, but become sinuous with embayments and arms of the sea that reach deeper into the continent. Where extension is concentrated, a future ocean outlines itself as a series of linked rift basins and incipient seaways. In summary, the outline of Pangea, through its lifetime, is a balance between persistence and gradual change. The supercontinent remains the dominant land feature on one side of the planet for a lengthy interval, but its precise shape position and internal geometry are not fixed. Plate motions, mantle flow, and crustal deformation continuously adjust the positions of coastlines, the widths of interior seas, the shape of the Tethys region, and the distribution of early rifts. The supercontinent that assembles in late Paleozoic time is thus not quite the same as the Pangea that enters the earliest stages of breakup in Triassic and early Jurassic time, even though both states share the same fundamental condition: most of Earth's continental crust joined into one large body that shapes the global geometry of land and ocean. When Pangea exists as a single broad landmass on one side of the planet Earth's atmosphere, still moves under the same basic physical rules that operate today. The planet rotates once every roughly 24 hours. The axis of rotation is tilted relative to the plane of its orbit, and the planet receives more solar energy at the equator than at the poles. Warm air near the equator rises and moves aloft. Cooler air near higher latitude sinks, and the rotation of Earth deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere. These simple facts give rise to a pattern of large circulation cells and wind belts that encircle the globe, In each hemisphere, a band of rising air near the equator feeds a system known as the Hadley cell, which carries air poleward aloft and returns it to the surface in the subtropics, where it sinks and flows back toward the equator as trade winds. Farther poleward mid-latitude circulation cells and polar cells operate, giving rise to belts of westerly winds and polar easterlies. Over an ocean-covered planet, these wind belts would be nearly zonal, meaning that they would run around the planet in nearly continuous east-west bands. With Pangea, the positions of these belts relative to land and sea change, and the land mass itself interacts with the moving air to create more complex patterns. But the underlying structure of trade winds, westerlies, and polar easterlies is still present. The equatorial region of Pangea, where the supercontinent crosses low latitudes, lies under the band of intense solar heating and rising air that defines the intertropical convergence zone. Here, warm surface conditions and strong evaporation over adjacent warm seas cause moist air to rise, cool, and condense. In the equatorial zone itself, near the line where ascending air dominates, surface winds tend to be weak and variable. On either side of this zone, however, the trade winds blow steadily. In the northern hemisphere, surface air in the Hadley cell flows from higher pressure subtropical regions toward the equator and is deflected to the right, forming the northeast trade winds. In the southern hemisphere, the same type of flow is deflected to the left, forming the southeast trade winds. Over the waters of Panthalassa and over the Tethys region, these trades drive broad belts of near-surface airflow that move from east to west. Where they encounter the coastlines of Pangea, they deliver moisture and momentum to the lower atmosphere above the land. Because Pangea covers a wide range of latitudes, the interaction of these trades with the supercontinent varies along its length. Near equatorial and low-latitude coasts, the trade winds may blow onshore or alongshore, depending on local geometry. Where the coastline is oriented north-south and lies just poleward of the equator, trades typically come in from the east, at an oblique angle carrying maritime air inland. Where the coastline is oriented differently, the flow may skim along the coast, influencing coastal upwelling and waves, but delivering less direct onshore flow. In general, however, the belts of trade winds define a lower atmospheric pattern in which warm, moist air is driven toward the western sides of ocean basins and toward parts of Pangea's low-latitude shores. Above these belts, air that has risen at the equator moves poleward in the upper troposphere and then sinks in the subtropics. At the surface, in these subtropical regions, a tendency toward high atmospheric pressure and descending dry air creates zones where clear skies and low precipitation are common in many climate states. On the flanks of Pangea that lie under these subtropical belts, surface winds shift from easterly trades to westerlies as one moves poleward. The westerlies are mid-latitude winds that flow from west to east in each hemisphere. They form part of the mid-latitude circulation cells which transport heat and moisture from lower latitudes toward the poles. Over ocean westerlies can maintain relatively continuous paths. But over a supercontinent, they encounter large expanses of land surface with variable elevation and surface properties. When these westerlies blow across the outer margins of Pangea and into its interior, they pass over coastal shelves, mountain belts, plateaus, and broad lowlands. The contrast between the thermal properties of land and ocean and the presence of major topography generates stationary waves and regional disturbances in the flow. These disturbances cause the wind belts to bend, tilt, and form large meanders rather than remaining perfectly zonal. At higher latitudes closer to the poles, polar easterlies blow from east to west, near the surface, reflecting cold, dense air that spills outward from polar regions and is deflected by rotation. In the Pangea interval, climate evidence suggests that the planet is in a greenhouse state with little or no large continental ice at the poles. But polar regions are still cooler than the equator and still act as sources of relatively cold air. Where polar air masses meet air from the westerlies, at mid-latitude strong horizontal temperature gradients form, helping to support jet streams in the upper atmosphere. Jet streams are narrow bands of strong winds that flow from west to east near the boundaries of major circulation cells. Their positions guide the paths of weather disturbances and influence storm tracks. Over Pangea, these jets do not follow smooth circles, but instead are steered and deformed by the distribution of highlands, lowlands, and adjacent ocean. The presence of Pangea as a single large heat source and heat sink also modifies the seasonal cycle of atmospheric circulation. Land heats up and cools down faster than ocean water. In a world of smaller continents, this leads to monsoon systems where summer heating over land reverses or strengthens local wind patterns. With Pangea, the supercontinent provides a very large area that experiences strong seasonal contrasts. During the summer of each hemisphere, regions of the supercontinent lying under high sun and long days warm strongly at the surface. Warm air rises, lowering surface pressure over the heated land relative to the surrounding ocean. Air from over Panthalassa and on the opposite side over the Tethys region is drawn toward the interior, bringing moisture-laden winds toward the continent. In winter, the pattern reverses land, cools faster than sea surface pressure over Pangea tends to rise compared with adjacent oceans, and winds from the interior blow outward toward the coasts. These seasonal reversals are strongest in low to mid-latitude sectors, where the contrast between land and sea temperature is greatest, and where the geometry of the coastline favors onshore flow during warm seasons and offshore flow during cool seasons. The result is a pattern of large-scale seasonal monsoon circulation systems along certain margins of Pangea, especially in the Tethys region and along parts of the eastern and western coasts that lie in low latitudes. Because Pangea extends far into the interior, however, air drawn inland during summer can travel very long distances before reaching the central parts of the supercontinent. Along the way, much of its moisture can be lost as precipitation on windward slopes or near the coast. As a result, while coastal and near-coastal areas may experience strong monsoon rains under the influence of these seasonal circulations, interior regions, under the same large-scale wind belts, can remain relatively dry. In the mid-latitudes, the presence of Pangea modifies the paths of storm systems that form along frontal zones between air masses. Cyclonic systems associated with contrasts between warm subtropical air and cooler polar air are guided by the westerlies and by the position of jet streams. When these systems approach Pangea, they encounter the thermal and topographic contrasts of the supercontinent. Warm continental interiors in summer can enhance rising motion and precipitation along fronts, while colder winter interiors can stabilize the atmosphere and suppress convection away from coastal regions. Mountain belts that run across the path of westerlies can also force air to rise on their windward sides and descend on their leeward sides, reinforcing patterns of wetter and drier regions within a given latitude band. Against a background of trade winds, westerlies and polar easterlies, the full atmospheric circulation over Pangea consists of large persistent features and shorter-lived weather systems. The persistent features include the approximate positions of the main circulation cells and wind belts set by Earth's rotation rate and heat distribution. The shorter-lived systems include storms, monsoon surges, and local wind patterns that arise from the interaction between large-scale flow and the detailed shape of the land. Climate models that place a Pangea like supercontinent on a rotating warm Earth and simulate atmospheric dynamics show that the zonal symmetry of the ideal three-cell pattern breaks down into a more complex arrangement of planetary waves and stationary highs and lows. However, these models still reproduce the core structure of equatorial rising motion, subtropical subsidence, mid-latitude westerlies, and polar flow. The uncertainties in these reconstructions concern the exact strengths and positions of features like jet streams, storm tracks, and monsoon centers for particular times within the Pangea interval. These details depend on specific greenhouse gas levels, surface elevation patterns, and the precise latitude and orientation of Pangea at each time slice. What is robust is the understanding that the atmospheric circulation over Pangea is organized by the same fundamental physics that operate today, but that the presence of one very large landmass on one side of the planet and one very large ocean on the other side produces a distinctive pattern of winds. In this pattern, broad belts of trades westerlies and polar easterlies still circle the globe, but they interact with the geometry of the supercontinent to create strong seasonal monsoon flows, stationary wave patterns tied to topography, and sharp regional contrasts between dynamic coastal atmospheres and more stable interior air masses. This is the large-scale movement of air over Earth during the time when Pangea exists. Along the margins of Pangea, where land meets the surrounding oceans and marginal seas, the interaction between seasonal heating of the supercontinent and the steady background wind belts produces strong patterns of monsoon circulation and marked contrasts between wet and dry seasons. The basic driver of these monsoons is straightforward. Land surfaces respond more quickly to changing sunlight than ocean surfaces do. As a result, when the part of Pangea in a given hemisphere tilts toward the sun during its summer season, the land there warms faster and to higher temperatures than the nearby ocean. Warm air over land expands and rises, lowering the surface air pressure. Over the adjacent ocean, where water warms more slowly and retains more heat over time, the air remains relatively cooler and denser. The pressure difference between the heated land interior and the surrounding sea sets up a large-scale flow of air from sea toward land near the surface. This is the summer monsoon phase. Moist marine air moves inland, and as it encounters elevated terrain and heated land surfaces, it continues to rise cool and condense water vapor into clouds and precipitation. In the winter season, when the same sector of Pangea tilts away from the sun, the situation reverses. Land cools more rapidly than the ocean, creating a relative high-pressure area over the interior and lower pressure over the warmer ocean. Near the surface, air then flows from land toward sea, and the moisture transport is directed outward. This is the winter monsoon phase characterized by drier conditions over much of the land and relatively more cloud and rainfall over adjacent waters. Because Pangea is very large, these seasonal shifts in circulation develop not just as local phenomena, but as continent-scale systems, whose influence can extend thousands of kilometers inland from the coast, although the strength of their moisture signal weakens with distance. The strongest monsoon systems during the Pangea interval likely occur where three conditions align. First, the coastline must lie in low to middle latitudes where solar heating is intense and seasonal changes in insolation are significant. Second, there must be a large continuous land area extending inland from the coast so that a broad region of heated or cooled surface can shape the pressure field. Third, there must be adjacent ocean or marginal seas that can supply moisture and act as relatively slow-responding thermal reservoirs. The Tethys region provides many such settings. Along the northern margin of Gondwana and the southern margin of the northern lobe of Pangea, belts of low to middle latitude coastline face shallow to deeper basins of the Tethys. In warm season months for that hemisphere, strong solar heating over these land surfaces raises temperatures and draws moist air inland from Tethyan waters. Climate models that place a Pangea-like landmass in this configuration produce broad monsoon circulation cells focused along these margins. Surface winds blow onshore in summer, bringing humid air that rises over coastal ranges and plateaus. Heavy seasonal rains fall on windward slopes, and runoff from these rains flows back toward the seas through dense networks of rivers. When the season turns surface, winds shift and blow more strongly offshore. The humid air retreats, the sky clears more often, and rainfall becomes sparse over much of the same region. A similar pattern appears along other low-latitude sectors of Pangea's coasts, though the exact positions and strengths of these monsoon systems vary with the orientation of the coastline and with the configuration of nearby basins. On the western side of the supercontinent facing Panthalassa, equatorial and low-latitude regions feel the influence of trade winds blowing from east to west. In the warm season, when the interior of these regions is strongly heated, the trades that approach the coast can be drawn inland, feeding a monsoon circulation in which moist marine air rises over land. On the eastern side, facing the great ocean and other sectors, mid-latitude westerlies and subtropical circulation patterns interact with seasonal heating of the land to produce different but related systems. In all these cases, the key effect is that parts of the margin experience a distinct alternation between a warm, wet season dominated by onshore flow and deep convection and a cooler, drier season dominated by offshore flow and more stable atmospheric conditions. Because a Pangea extends far into the interior, the strength of monsoon rainfall declines with distance from the coast. Moist marine air loses water as it is forced to rise over coastal ranges and highlands. This process not only deposits large totals of rain near the coast, but also dries the air that continues inland beyond the topographic barrier. On the windward sides of mountains, thick clouds frequent storms, and persistent rainfall are common in the monsoon season. On the leeward sides, subsiding air warms and dries, creating rain shadow zones. Over Pangea, these rain shadows can be very extensive because mountain belts are long and continuous. For example, the central Pangean range formed by the collision of earlier continental blocks and roughly tracing a line through what will one day become eastern North America, northwestern Africa, and parts of southern Europe acts as a major barrier to low-level flow. When monsoon winds from Tethyan waters move inland toward this range, they deposit much of their moisture on the seaward slopes. The air that spills over into the interior is considerably drier, contributing to arid regions and deserts in the continental center. Thus, even though a strong summer monsoon may exist along a given coast, the inland side of major mountain belts can remain dry throughout much of the year. Seasonal contrasts in temperature over Pangea are also sharpened by its large size and by the absence of moderating ocean influences in the interior. Near the coast, sea breezes and the thermal inertia of nearby water bodies help smooth daily and seasonal temperature swings. Inland, especially at mid-latitude, summers are hotter and winters colder because there is only land to absorb and release heat. This continentality enhances the pressure differences that drive monsoon circulations. In summer, very warm interiors develop low surface pressure that pulls in moist air from great distances. In winter, cold interiors build strong, high-pressure systems that favor persistent outward flow of dry continental air. These interior high-pressure systems can expand and shift, pushing dry air masses over adjacent coastal regions and suppressing rainfall, even in areas that otherwise lie under moist flow from the ocean. The balance between these tendencies differs from place to place, but the general result is that the margins of Pangea show strong seasonal contrasts in both temperature and precipitation. Another important aspect of these monsoon and seasonal patterns is their interaction with the prevailing wind belts described earlier. The background trade winds and westerlies do not disappear during monsoon phases. Instead, they are redirected and strengthened or weakened in different sectors. For instance, when a large summer low-pressure area forms over a low-latitude section of Pangea, the trades in the adjacent ocean can be drawn more strongly toward the continent, increasing low-level convergence of moist air and deep convective activity. This can shift the position of the main rainfall belt associated with the intertropical convergence zone toward the heated landmass, further enhancing seasonal rains there. In mid-latitudes, the position of jet streams and storm tracks can respond to changes in the temperature contrast between land and sea. Warm continental surfaces in summer can cause the upper-level jets to meander differently, possibly favoring certain coastal regions for more frequent storms and leaving others in relative subsidence and clear skies. In winter, cold continental surfaces can strengthen baroclinic zones, the regions of sharp temperature contrast that support the growth of cyclones and thus influence where extratropical storms travel and where their associated rainfall reaches land. While there is uncertainty in modeling the exact details of these atmospheric responses, the robust outcome is that the geometry of Pangea, with its broad interior and long coasts at a range of latitudes, supports several large monsoon systems that are embedded within the global pattern of trade winds and westerlies. Over the full time span that Pangea exists, these systems do not remain static. Changes in the position of the supercontinent relative to the equator, variations in greenhouse gas levels, and gradual adjustments in topography alter the strength and reach of monsoon circulations. In some intervals, evidence from sedimentary rocks and fossil soils points to particularly intense seasonal rainfall in certain regions with thick successions of river deposits and floodplain mudstones that show repeated wetting and drying. In other intervals, more persistently arid conditions appear, suggesting weaker or more distant monsoon influence. Despite these changes, the core pattern holds along many margins of Pangea. Summers are dominated by onshore flow of moist air and heavy rainfall on windward coasts and slopes, while winters are dominated by offshore flow of dry air and reduced precipitation. Inland behind the shields of long mountain belts, the supercontinent's size and distance from the sea limit the reach of moist monsoon air, creating strong spatial gradients in rainfall and in the contrast between wet and dry seasons. These gradients are an important part of how the atmosphere over Pangea distributes water vapor and latent heat, and set the stage for the land surface climates that develop on the supercontinent's margins and interiors. Across the broad interior of Pangea, far from the softening influence of surrounding seas, the behavior of the atmosphere produces climates that are markedly drier than those at the margins. The same circulation patterns that send moist air onto some coasts and up the windward slopes of mountain belts also remove much of that moisture before the air can reach the center of the supercontinent. What arrives over the continental heartland is air that has already lost a large fraction of its water vapor, and that often descends rather than rises. This combination of prior rainout and subsidence favors clear skies, strong sunshine at the surface, and low overall precipitation. In the low to middle latitude, belts where Pangea's interior lies beneath parts of the Hadley circulation and adjacent circulation cells, descending branches of these cells reinforce dryness. Air that has risen near the equator and moved poleward aloft eventually sinks in subtropical regions. When this air returns to the surface over land, it warms as it compresses, lowering relative humidity and inhibiting cloud formation. Over an ocean, this sinking air can still pick up moisture from the surface and contribute to subtropical high-pressure systems above relatively calm, clear seas. Over the interior of Pangea, where there is little open water, the same sinking air crosses mostly dry ground and gains little moisture. As a result, large areas under these descending branches become domains of persistent dryness, with only occasional disturbances bringing significant rainfall. The presence of long mountain belts on Pangea strengthens this contrast between wet margins and dry interiors. When moist air from Panthalassa or the Tethys region is drawn inland by monsoon circulations or by the approach of mid-latitude storms, it is forced to rise over the seaward slopes of high ranges, such as the central Pangean mountains. As this air rises, it cools and condenses water vapor, releasing latent heat and producing clouds and precipitation. Much of the moisture is deposited as rain or snow on the windward side. Once over the crest, the air descends along the leeward slopes and into the interior. During descent, it warms, and its relative humidity falls, further reducing its capacity to produce rain. This rain shadow effect creates sharp gradients in precipitation across distances that are modest on the scale of the supercontinent, but large enough to separate humid foothills from arid basins. In a world where the main land mass extends for many thousands of kilometers, such rain shadows can merge and spread until much of the inner continent lies in the lee of some mountain chain with respect to prevailing winds. Beyond the influence of individual ranges, the very width of Pangea ensures that interior regions are remote from any oceanic moisture source. Air masses that travel from one coast to the center must cross long stretches of land. Even if they begin as humid marine air, each encounter with topography, each episode of rising motion and precipitation, and each night of radiative cooling over land removes more water vapor. By the time these air masses reach the deep interior, they may be dry enough that only a small fraction of days in a year host any rainfall at all. The term continentality is used to describe climates where temperature and humidity respond strongly to conditions over land rather than ocean. Pangea's interior shows extreme continentality. In summer, when the interior under clear skies receives intense solar radiation and has limited evaporative cooling, because surface water is scarce, daytime temperatures can rise to high values. At night, the same clear skies and dry air allow rapid loss of heat to space, so temperatures can drop sharply. In winter, the absence of nearby warm seas means that cold air can accumulate and persist. These strong seasonal and daily temperature ranges enhance the formation of surface high-pressure systems during cold periods and low-pressure troughs during hot periods. But because moisture is limited, the atmospheric response often yields changes in wind without large increases in rain. The distribution of dry air and clear skies over much of the interior also allows strong solar heating of the ground surface, which promotes thermals or rising plumes of warm air during the day. These thermals can lift dust and fine particles from the surface into the lower atmosphere, especially in regions where loose sediments are exposed and vegetation cover is sparse. On Pangea, large inland basins with limited runoff and high evaporation rates can accumulate fine sediments such as silt and very fine sand. Under the action of dry winds and daytime heating, these materials can be lofted into the air and transported over long distances. The resulting dust loading further influences the radiative balance of the atmosphere by scattering and absorbing sunlight and by providing particles around which any available water vapor can condense. In practice, however, the overall scarcity of moisture in these regions means that the net effect is often hazy skies rather than widespread cloud decks or rain. The structure of the boundary layer, the lowest part of the atmosphere directly influenced by the surface in these dry interiors, tends to favor deep daytime mixing and shallow stable layers at night. During the day, surface heating creates a thick mixed layer in which turbulent motions can homogenize temperature and humidity over hundreds of meters to a few kilometers in height. This mixed layer spreads heat upward and can distribute any pollutants or dust through a deep column of air. At night, surface cooling under clear skies can create a shallow inversion layer where air near the ground is colder than the air just above. This inhibits vertical mixing and can trap any locally generated moisture or aerosols near the surface. Such diurnal cycles are characteristic of arid continental regions and would be pronounced over Pangea's central deserts and semi-deserts. The pathways of large-scale weather systems into the interior are also affected by the configuration of land and highlands. Mid-latitude cyclones that form along temperature fronts between different air masses tend to travel along storm tracks shaped by the jet streams. Where these tracks intersect, the coast of Pangea storms can bring bursts of rainfall and strong winds to coastal and near-coastal areas. However, as these systems move inland over increasingly dry and uniformly heated surfaces, the contrasts in temperature and moisture that gave them strength can weaken. Without access to new sources of moisture from warm seas, their clouds thin and their precipitation diminishes. Only the most intense disturbances, or those that are able to tap moisture along river corridors or from residual shallow seas, are likely to maintain significant rainfall far into the interior. Over long time scales, these atmospheric patterns leave signatures in the rocks of Pangea's interior. Thick successions of wind-blown sand, preserved as large-scale cross-bedded sandstones, indicate the presence of extensive dune fields built by persistent winds in arid settings. Layers of fine-grained wind deposited silt, known as loess record episodes, when strong winds transported dust from bare surfaces over wide regions. Evaporate deposits such as layers of salt and gypsum in ancient basins show that in some low-lying inland areas, water supplied by occasional rains or inflowing rivers evaporated faster than it was replenished, leaving behind dissolved minerals. These geological indicators confirm that many parts of the Pangean interior spent long periods under dry evaporation-dominated atmospheric regimes. The uncertainties in reconstructing the exact placement and size of all dry zones are linked to uncertainties in the positions of mountain belts, the height of plateaus, and the precise path of prevailing winds at different times. Climate models that place a Pangea like landmass under estimated greenhouse gas levels and solar output help identify likely patterns belts of aridity, centered in subtropical to mid-latitude interiors, rain-shadow deserts behind major mountain chains, and some seasonal rainfall along transient storm tracks. These simulations, combined with sedimentary evidence, support a picture in which the atmosphere over Pangea produces strong spatial contrasts in humidity, with wet coastal monsoon belts and more temperate maritime margins grading inward to semi-arid steppe regions and then to very dry cores. The evolution of these patterns through time depends on slow changes in continental position and relief. But throughout the interval when Pangea exists, the dominance of one large landmass ensures that the atmosphere has ample scope to create broad, persistent continental interiors where subsiding dried air and long land pathways keep rainfall low and the climate dry for much of the year. Around the margins of Pangea, the broad Panthalassa Ocean and the more complex Tethys region together define the main pathways by which water moves, heat is redistributed, and the sea interacts with the supercontinent. Panthalassa covers almost the entire hemisphere opposite Pangea. Its surface is not still. Winds described earlier push on the water, and the rotation of Earth deflects moving flows so large gyres or rotating current systems fill the ocean basins. The trade winds in low latitudes blow from east to west on both sides of the equator, driving warm surface water toward the western parts of the ocean. In mid-latitudes, westerlies blow from west to east and drive surface waters in the opposite direction. Together with the effects of the planet's rotation, these wind patterns generate broad basin-scale gyres that circulate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. In Panthalassa, each hemisphere hosts a large subtropical gyre with warm western boundary currents and cooler eastern boundary currents, much as modern oceans do, but on a larger and more continuous scale because there are fewer continental barriers. Near the equator, the convergence of the northeast and southeast trade winds produces a strong westward flow, an equatorial current that sweeps warm water across the low-latitude ocean toward the side where Pangea lies. This current carries heat from the sunlit central and eastern parts of Panthalassa toward the Western Ocean and into contact with the supercontinent's low-latitude coasts. When this warm westward moving water reaches land, it has to turn. In the northern hemisphere, part of it is deflected poleward along the western edge of Pangea, forming a warm boundary current that flows toward higher northern latitudes along the continental margin. As it moves poleward, this current gradually cools and interacts with mid-latitude westerlies, turning eastward and then equatorward around the northern subtropical gyre before eventually feeding back into the equatorial zone. In the southern hemisphere, a corresponding pattern develops warm water carried to the western margin of the supercontinent. At low latitudes turns poleward along the coast, cools as it flows into higher latitudes, and then returns to equatorward along the eastern side of the gyre. The exact shapes and positions of these gyres depend on the placement of land ridges and deep basins in Panthalassa. But the broad picture is of large rotating systems that set the basic directions of surface flow and control where warm and cool currents touch the continents. The western boundary currents are typically faster and deeper than the eastern ones. They concentrate heat transport and bring warm water toward mid-latitudes. In contact with the coastal margins of Pangea, such currents can raise sea surface temperatures and increase evaporation in adjacent regions, supplying moisture to the atmosphere that later falls as rain on land. Eastern boundary currents, by contrast, often flow over upwelling zones, where deeper, cooler water rises toward the surface as winds drive surface water away from the coast. In Panthalassa, where long stretches of coastline can lie under wind patterns that favor such upwelling, cold, nutrient-rich water, can reach the surface and flow equatorward along the margin of Pangea. This combination of warm western boundary currents and cool eastern boundary currents means that the coastal seas around the supercontinent are not uniform in temperature. Some margins, especially those receiving poleward flow of warm water, are comparatively mild even at higher latitudes, while others, especially those facing equatorward cold currents, are cooler and more prone to upwelling. Beyond the subtropical gyres at higher latitudes, surface currents interact with strong westerly winds and with the edges of polar gyres near the poles. In these regions, the ocean meets colder air masses, and seasonal sea ice may form in some intervals, depending on global climate state, although during the warmest greenhouse times of Pangea, evidence suggests that large permanent sea ice caps are not present. Where surface water cools strongly and becomes dense, it can sink and form part of the deeper ocean circulation. In Panthalassa, with its enormous volume and relative lack of constrictions, such deep water formation sites help set up slow three-dimensional patterns of movement, in which dense water sinks in some high-latitude regions, flows along the deep ocean floor, and slowly upwells elsewhere, including along the eastern margins of gyres and near mid-ocean ridges. This overturning circulation connects surface and deep waters on time scales of many hundreds to thousands of years, and plays a role in distributing heat, carbon, and oxygen through the ocean interior. Within Panthalassa, the seafloor is not flat. Long mid-ocean ridges where new oceanic crust forms deep trenches, where old crust sinks back into the mantle, and plateaus built by volcanic activity create a complex bathymetry. These features steer deep currents, redirecting flow along certain paths and creating regions where mixin is enhanced or reduced. Over ridges and rough topography, tides and large-scale flows can generate internal waves and turbulence that stir the water column, helping to move nutrients and gases between layers. In deep basins, separated by sills or elevated ridges, water can become more isolated, with slower renewal and potentially lower oxygen levels. The details of this deep circulation and its variation through the lifetime of Pangea involve uncertainties, because the exact configuration of seafloor features and deep water formation sites can change as plates move and as global climate state shifts. However, the broad concept of a large wind-driven surface circulation linked to a slower overturning circulation in the deep ocean applies to Panthalassa as it does to modern oceans. On the side of Pangea, where the Tethys region lies, the circulation pattern is more intricate because the geometry of land and sea is more broken. The Tethys during the Pangea interval is expressed as a belt of marginal and interior seas between the northern and southern parts of the supercontinent, often including several connected basins, separated by shallow sills or by chains of islands and microcontinents. Surface winds blow over these basins in patterns influenced by latitude and by the shapes of the coastlines. Where the Tethys basins lie in low latitudes, trade winds drive westward surface flow and help form smaller gyres within each sub-basin. In some sectors, water from Panthalassa enters the Tethys through straits or gaps between continental blocks, carrying properties such as temperature and salinity from the open ocean into these more enclosed seas. In others, Tethyan water may spill back out toward Panthalassa. The presence of sills with limited depth means that deep water exchange between the Tethys basins and the open ocean can be restricted. This can lead to differences in temperature and salinity structure between Tethys and Panthalassa, particularly if evaporation and freshwater input within the basins are not balanced. In warm climates, with high evaporation over the Tethys surface and limited river input, surface waters can become more saline, and denser water may form and sink, driving internal overturning. Alternatively, in sectors where monsoon rains and river discharge are strong, surface waters can be fresher and less dense, favoring a different vertical structure. In all cases, the currents within the Tethys basins are constrained by basin outlines and by the presence of sills, so that flow may recirculate locally in gyres rather than directly joining the broad Panthalassa circulation. Around the margins of Pangea that face Tethys, boundary currents and exchange flows through narrow seaways influence coastal conditions. Warm saline water may flow along one side of a basin, while cooler or fresher flows occupy another side. Wind-driven upwelling can occur where surface water is driven away from a coast by the local wind direction, bringing deeper water upward. Because the Tethys region includes many shallow shelves and platforms, especially along the edges of microcontinents and continental promontories, a significant fraction of its area is covered by relatively shallow, sunlit water. In these shallow environments, interaction between tides, waves, and currents produces complex patterns of circulation at small scales. In the open reaches of Panthalassa, sea level relative to Earth's center of mass is set by the balance between the volume of ocean water, the shape of the ocean basins, and dynamic effects such as the piling up of water in gyres. Over the time span when Pangea exists, longer-term changes in mid-ocean ridge activity and in the storage of water in any remaining ice also adjust average sea level. On shorter timescales, wind-driven setup along coasts and standing waves in semi-enclosed basins can tilt the sea surface slightly and thus affect current strength in straits and along shelves. These details add complexity to the circulation around Pangea, but do not change the central picture that the main oceanic setting is a vast panthalassa, with large subtropical gyres flanked on one side by the more segmented Tethys region, with its own internal currents and constrained exchanges. The way in which ocean currents during the Pangea interval interact with the supercontinent's margins has measurable consequences for the distribution of temperature and for the delivery of moisture to the atmosphere, but the focus here remains on the physical movement of water itself. In summary, the seas of the Pangea world are organized into a dominant wind-driven surface circulation in panthalassa, with subtropical and subpolar gyres structured by trade winds and westerlies, and into more complex basin scale flows within the Tethys region. Warm boundary currents carry heat poleward along some coasts of the supercontinent, cool boundary currents and upwelling influence others, and deep overturning connects surface and abyssal waters over long periods. Against this large-scale background, local tides, waves, and smaller currents shaped by shelves, ridges, and sea mounts further refine the movement of water near Pangea's shores and within its interior seas, giving the planet's hydrosphere a dynamic structure during the time when the supercontinent exists. Within the oceans that surround and infiltrate the margins of Pangea, the movement of water is not only horizontal along the surface, but also vertical, linking sunlit surface layers to darker deep layers, and setting the conditions under which marine life can obtain oxygen. The basic structure of the water column in Panthalassa and in the Tethys basins reflects differences in temperature and salinity from top to bottom. Warmed by sunlight and in contact with the atmosphere, the upper ocean is typically lighter, while deeper water is colder and often slightly more saline, making it denser. This contrast leads to stratification, a layered arrangement in which light surface water overlies denser deep water. Where stratification is strong, mixing between layers is limited, and exchange of oxygen and nutrients is reduced. Where stratification is weaker, or where physical processes overcome its surface, and deep waters can exchange more readily. The shape of the ocean basins and the presence of broad shelves, interior seaways, and constricting sills control how and where this vertical exchange occurs during the time when Pangea exists. In Panthalassa, the great size of the basin allows deep water masses to form in some high and mid-latitude regions where surface waters cool and become dense enough to sink. In these areas, especially where cold winds and strong heat lost to the atmosphere remove warmth from the surface, and where evaporation or brine rejection from seasonal sea ice increase salinity, the upper layer can gain density until it plunges downward, carrying oxygen from the atmosphere into the deep ocean. This process, often called deep water formation, is not uniform around the basin. It tends to occur where the combination of temperature, salinity, and basin geometry favors sinking. Once formed, deep water spreads along the seafloor and slowly fills the deeper parts of Panthalassa. Over time, it gradually mixes with older deep water, and its oxygen is consumed as organisms in the dark ocean respire and as sinking organic matter from the surface is decomposed. Far from its formation, regions deep water in the most remote parts of the basin can become relatively low in oxygen before it eventually returns toward the surface through slow upwelling. Upwelling is the process by which deeper water rises toward the surface to replace water that is moved away by winds or currents. In Panthalassa, winds that drive surface currents away from certain coasts or away from the equator create regions of divergence at the surface. In these regions, mass balance requires that deeper water move upward to fill the space left behind. Along eastern boundaries of subtropical gyres where winds and the rotation of Earth combine to push surface water offshore, long belts of upwelling can form. In low latitudes near the equator, where trade winds blow in opposite directions on either side of the equator surface, waters can be drawn away from the equatorial line, again allowing deeper water to rise. When deep or intermediate waters rich in nutrients reach the sunlit surface, they can support high rates of primary productivity. But if these waters are relatively low in oxygen, they can also create oxygen-poor zones just below the surface as organic matter produced in the upper ocean sinks and decays. The balance between nutrient supply, biological production, and ventilation from the atmosphere determines how far these oxygen minimum zones extend. The topography of the seafloor influences the paths of both deep currents and upwelling. Mid-ocean ridges that run through Panthalassa stand as long submarine mountain chains. As deep water flows across them, it is steered along valleys and over gaps. Rough topography enhances mixing, which can add oxygen to deeper layers by stirring them with more recently ventilated waters. In contrast, deep basins that are partly enclosed by ridges or plateaus with only shallow sills linking them to the wider ocean can trap dense water masses for longer periods. In such basins, if the rate at which oxygen is consumed exceeds the rate at which oxygen-rich water can enter across the sills or mixed downward from above, oxygen levels can fall significantly. In extreme cases, water at depth can become anoxic, meaning that it contains little or no dissolved oxygen. Evidence from the rock record indicates that such low oxygen conditions did develop in parts of the Panthalassa Basin during some intervals within the lifespan of Pangea, although the exact extent and timing of these events are still the subject of study. The Tethys region, with its series of connected basins, shelves, and seaways between the northern and southern parts of Pangea, shows even stronger sensitivity to basin geometry. Many Tethyan basins are relatively shallow compared with the deepest parts of Panthalassa and are bordered by wide continental shelves. These shelves are flooded extensions of the continents where water depths are modest and sunlight can reach the seabed. Here, tides, waves, and wind-driven currents can efficiently mix the water column so that surface and bottom waters exchange oxygen more readily. In such well-ventilated shallow seas, oxygen tends to reach the full depth of the basin, supporting benthic communities on the seafloor. However, where shelves step down into deeper subbasins separated by sills, vertical and horizontal exchange can become more restricted. A shallow sill sets the maximum depth at which water from the open ocean can flow into the basin. If water below sill depth in the basin is isolated from direct contact with the better ventilated waters outside, then its renewal depends on occasional overflow events or on slow diffusive mixing. In a warm world with high rates of organic production in the surface layer, the sinking and decay of organic matter can remove oxygen from these deeper waters faster than it is replenished. This process can lead to stratified basins, in which a surface layer remains oxygenated, while underlying layers become progressively oxygen depleted. In more extreme cases, sulfur-bearing bacteria can thrive in these anoxic bottom waters, altering their chemistry further. Sediments deposited under such conditions are often rich in organic matter and show features that indicate deposition in low oxygen or anoxic environments. During the Pangea interval, several episodes of widespread low oxygen conditions in the oceans, sometimes described as oceanic anoxic events, are recorded by black shales and other sedimentary markers in both Tethyan and Panthalassan settings. The end, Permian and Triassic to Jurassic boundaries, for example, are associated with strong disruptions to the marine carbon and sulfur cycles and with signs of expanded anoxic zones. The exact mechanisms driving these events likely involve multiple factors, including changes in global temperature weathering rates on land nutrient delivery to the seas and volcanic outgassing. But the basin shapes and sill depths of Pangea's oceans set the stage on which these processes act. In general, narrow interior seaways and semi-enclosed basins are more prone to developing oxygen-depleted bottom waters than open, well-connected, deep oceans, especially when surface productivity is high and when stratification suppresses vertical mixing. Along the continental shelves that fringe Pangea, the interaction between river input tides and coastal currents shapes another dimension of the oxygen story. Rivers that drain the supercontinent carry freshwater sediments and dissolved nutrients into marginal seas. The input of buoyant freshwater can create a surface layer that is less dense than the saltier water below, sharpening stratification near the coast. If winds and tidal mixing are strong enough, this stratification can be broken, and oxygen from the atmosphere can reach deeper layers. If not, the combination of nutrient-rich river input and stable stratification can favor intense biological production in the surface layer and subsequent oxygen consumption at depth. Some shelf regions under such conditions can host seasonal or persistent oxygen minimum zones in subsurface waters. Because Pangea is large, the total length of its coastlines, and the variety of shelf configurations are considerable, so different margins can experience varying degrees of stratification and ventilation at the same time. In the open reaches of Panthalassa, away from shelves and sills, the deep ocean is supplied with oxygen primarily by the sinking of surface waters in high and mid-latitude formation regions, and by the slow upwelling of water elsewhere. As long as the rate of new deep water formation and the rate of mixing are sufficient, most of the deep basin remains at least moderately oxygenated, even though oxygen concentrations decline along the flow paths. Where formation weakens, where stratification strengthens because of warming or freshening at the surface, or where organic matter flux from the surface increases over large areas, the volume of low oxygen water can expand. Models of ocean circulation for Pangea, like configurations together with geochemical data from sediments, support a view in which the balance between ventilation and consumption shifts over time, sometimes allowing well-oxygenated conditions and sometimes permitting broad expansion of oxygen-poor waters. The details of this balance are still uncertain for many time slices, but the role of basin shape shelves and sills in modulating vertical exchange is well established. Taken together, these processes mean that the oceans around Pangea are not uniform reservoirs of breathable water for marine organisms. Instead, they are structured in three dimensions: by temperature and salinity-driven stratification, by wind, driven upwelling and downwelling, and by the constraints of basin geometry. Deep currents carry oxygen from a few key formation regions into the abyssal panthalassa. Upwelling returns older, often oxygen-depleted waters to the surface in specific belts. Shelves and marginal seas range from well-mixed and fully oxygenated to stratified and anoxic, depending on depth, sill structure, and organic loading. The distribution of oxygen through this system defines where in the vertical column marine animals and plants can live comfortably, where they must tolerate lower oxygen levels, and where conditions at depth become inhospitable during the long interval when Pangea exists. During the main interval, when Pangea exists as a joined landmass, Earth is in a climate state that is warmer than today, and that can be described as greenhouse rather than icehouse. In an icehouse state, large permanent ice sheets occupy polar regions, and sea level is relatively low because much water is stored on land as ice. In a greenhouse state, permanent ice is greatly reduced or absent outside high mountains, and sea level is higher because most water resides in the oceans. For the late Permian and much of the Triassic and early Jurassic, multiple lines of evidence point to a greenhouse world. Estimates of atmospheric carbon dioxide based on the chemistry of ancient soils, the density of pores in fossil leaves, and the composition of marine carbonates suggest that average carbon dioxide concentrations during key parts of the Pangea interval are several times higher than pre-industrial values. Values of roughly 1,000 to 2,000 parts per million appear in many reconstructions for the early to middle Mesozoic, though with significant uncertainties and regional variations. These elevated greenhouse gas levels enhance the trapping of outgoing long-wave radiation and raise global mean surface temperature compared with a world that has the same solar input but lower carbon dioxide. Climate model experiments using plausible reconstructions of carbon dioxide and the geometry of Pangea typically produce global mean surface temperatures a few degrees Celsius higher than modern values, with some simulations suggesting differences of around 3 to 6 degrees Celsius. The polar regions in these models are considerably warmer than today, reducing the equator to pole temperature gradient. Rock and fossil evidence supports this picture. In high-latitude regions that at the time lie near the poles while attached to Pangea or near its margins, sedimentary deposits contain plant fossils and geochemical signatures that indicate relatively mild, even temperate, to warm conditions, rather than the presence of large ice sheets. In some Triassic strata from high northern and southern paleolatitudes, assemblages of plants suggest the presence of forests adapted to cool but not glacial climates. Glacially carved landforms and widespread glacial deposits, which are abundant in late Paleozoic rocks recording an earlier ice age, are notably scarce in younger Pangean successions, except locally in high mountain settings. This suggests that by the time Pangea is fully assembled and enters its main interval, large stable ice sheets at sea level are absent, and any ice exists primarily in higher mountain belts or as seasonal snow. In such a greenhouse state, the pattern of heat across the planet is set by the balance of incoming solar radiation, outgoing long-wave radiation, atmospheric and oceanic transport, and the distribution of land and sea. The equator still receives more solar energy per unit area than the poles. So the basic tendency is for warm air and surface waters to form at low latitudes and for heat to be transported poleward. However, with higher greenhouse gas concentrations, the atmosphere retains more heat, especially in high latitudes. This reduces the temperature contrast between equator and poles relative to a lower carbon dioxide world. As a result, polar regions are warmer, winters are milder, and the seasonal freezing and thawing of water is less extensive. The absence of large ice sheets also means that the surface reflectivity in high latitudes is lower than it would be with permanent ice cover. Exposed rock soil and vegetation absorb more solar energy than ice and snow, further supporting warmer conditions. Over Pangea itself, the pattern of heat is shaped by both latitude and continentality. Near the equator, parts of the supercontinent experience high annual solar input and relatively small seasonal changes in day length. With greenhouse warming and limited cloud cover, in some interior regions, surface temperatures there can be high, especially in deserts and semi-deserts where evaporative cooling is limited by scarce surface water. In mid-latitudes, seasonal contrasts are stronger. Summers over the continent can become very warm because land surfaces heat rapidly under long days and strong sun, while winters can be cool to cold, though not as severe as in an icehouse world at the same latitude, because background greenhouse warming limits the extent of cold air masses, and there is no thick, permanent ice to maintain very low surface temperatures. At higher latitudes on Pangea, conditions depend on proximity to the sea and on local topography. Coastal areas that receive warm currents from Panthalassa or from the Tethys region can experience relatively mild climates, despite their latitude with limited seasonal snow and ice. Continental interiors at similar latitudes but far from moderating seas can have colder winters and warmer summers reflecting strong continentality. Even so, the absence of extensive land-based ice sheets implies that average annual temperatures remain above the threshold needed to sustain long-lived ice over broad, low-lying areas. The vertical structure of the atmosphere also reflects greenhouse conditions. Warmer surface temperatures increase the amount of water vapor that the air can hold, and higher evaporation from warm seas and warm, moist coastal regions raises water vapor concentrations in the lower troposphere. Water vapor is itself a greenhouse gas, so this amplifies warming in a feedback loop, although the extent of this feedback is moderated by cloud formation and by dynamical processes that transport water vapor and heat. In warm climates, deep convective clouds in the tropics can both reflect more solar radiation back to space and trap infrared radiation, with the net effect depending on cloud properties and coverage. In mid-latitudes, storm systems and frontal zones transport heat poleward and redistribute water vapor. Pangea's size affects how these processes are expressed over land. Wide interior regions lack the abundant surface water that would otherwise feed high humidity and frequent cloud cover. As a result, clear skies and strong solar heating are common in these areas during the warm season, allowing surface temperatures to climb. At the same time, air masses moving over dry surfaces pick up less moisture, so even with elevated global water vapor, relative humidity in the lower troposphere over the interior can be modest, especially away from major rivers or residual lakes. Ocean temperatures around Pangea respond more slowly to seasonal forcing because water has a high heat capacity. In warm greenhouse intervals, modeled sea surface temperatures at low latitudes can be in the high 20s to low 30s in degrees Celsius, while high latitude sea surfaces might remain above freezing year-round. This reduces the capacity of the system to generate cold, dense surface water in high latitudes. Deep water formation needed to ventilate the deep ocean may shift to slightly lower latitudes or rely more on changes in salinity, such as those produced by evaporation or by brine rejection, where any seasonal sea ice still forms. The overall flattening of the equator to pole temperature gradient reduces the available potential energy for some atmospheric circulation features, but is counterbalanced by strong land-sea contrasts and by the presence of a large supercontinent that encourages strong stationary waves and monsoon systems. Over the full span of Pangea's existence, greenhouse conditions are not completely uniform. The late Carboniferous and early Permian record an earlier time when large ice sheets exist on parts of Gondwana, signaling a relatively cooler, more icehouse-like state. As Pangea assembles and time moves into the middle and late Permian, and then the Triassic, evidence suggests that these ice sheets retreat and disappear, and that the climate warms toward a greenhouse mode. Within this warm interval, there are still fluctuations in temperature on multi-million-year time scales, driven by changes in volcanic outgassing of carbon dioxide weathering rates on land, the burial and oxidation of organic carbon, and shifting continental positions. These swings can shift the exact values of global mean temperature and the strength of the equator to pole gradient, but do not re-establish large stable ice sheets over broad low-latitude regions. Thus, for much of the time when Pangea stands as a unified continent, Earth's climate can be described as a warm, largely ice-free state with high atmospheric carbon dioxide, mild to warm polar climates, and strong land-sea thermal contrasts. The pattern of heat is one in which equatorial regions are hot mid-latitudes on land experience strong seasonal temperature cycles, with hot summers and cool to cold winters, and high latitudes are cool but not dominated by massive ice. This pattern of temperature, combined with the atmospheric and oceanic circulation described earlier, sets the background against which more specific climate states episodes of relative cooling or warming sea level changes and the limited presence of ice and snow at the margins and on high ground evolve during the lifetime of Pangea. Over the long span of time, when Pangea exists as a joined landmass, Earth's climate does not remain at a single fixed state. Instead, the warm greenhouse background described earlier is shaped by slower and faster swings in temperature, moisture, and sea level that occur on time scales from tens of thousands to many millions of years. These swings arise from changes in greenhouse gas concentrations, from the slow rearrangement of continents and ocean basins, from variations in volcanic outgassing and rock weathering, and from orbital variations that adjust the distribution of sunlight through the seasons. Against this moving background, the planet remains mostly free of large low-latitude ice sheets, but traces of cold conditions persist in certain intervals and locations, especially in the early history of Pangea and at high elevations. At the start of Pangea's existence, the climate system is still adjusting from an earlier time of extensive glaciation on parts of Gondwana. In the late Carboniferous and early Permian, before the supercontinent reaches its mature configuration, large ice sheets occupy high latitude and high elevation regions in what will become South America, Africa, India, Australia, and Antarctica. As Pangea assembles, and as atmospheric carbon dioxide gradually rises due to volcanic outgassing and reduced burial of organic carbon, these ice sheets retreat. The transition from this cooler icehouse influenced state to a full greenhouse state occurs over tens of millions of years. By the time the classic Pangean arrangement is in place and the late Permian and Triassic intervals unfold, permanent continental ice sheets have largely vanished and the planet's climate is dominated by warm conditions, though local cold remains possible in high mountains and during winter seasons at higher latitudes. Even within this broadly warm mode, the climate does not remain uniform. Changes in the long-term balance between volcanic input of carbon dioxide and its removal by silicate rock weathering and carbonate burial can shift global temperatures upward or downward. When volcanic activity associated with mountain building and large igneous provinces increases, more carbon dioxide enters the atmosphere. If this input exceeds the long-term removal rate, greenhouse warming strengthens and global mean temperature rises. When uplifted mountain belts and exposed continental shelves enhance chemical weathering, more carbon dioxide is consumed and the climate can cool. On time scales of millions of years, these processes contribute to differences between relatively warmer and cooler phases within the Pangea interval. Geological evidence for such swings includes changes in the types of fossil plants and animals present at given latitudes, shifts in the distribution of climate-sensitive sediments, such as coals and evaporites, and variations in stable isotope ratios in marine carbonates that reflect changes in global temperature and ice volume. Superimposed on these long-term shifts are shorter period variations linked to Earth's orbital parameters. Small predictable changes in the shape of Earth's orbit, the tilt of its axis, and the timing of the seasons relative to its position around the Sun alter the seasonal and latitudinal distribution of incoming solar radiation. These orbital variations, often grouped under the term Milankovitch cycles, operate even when Pangea is present. They can modulate the intensity of monsoons, the strength of seasonality in temperature and rainfall, and the likelihood of snow and ice accumulation in high-latitude regions or on high ground. In sedimentary rocks deposited on land and in shallow seas around Pangea, rhythmic patterns in layer thickness and composition suggest that climate responds to these orbital cycles with wetter and drier or warmer and cooler intervals, recurring on 100,000-year scales. In the greenhouse world of Pangea, these orbital cycles do not typically generate large ice sheets, but they can influence the size of seasonal snowpacks, the extent of small mountain glaciers, and the timing and strength of monsoon rains. Sea level responds both to these climate swings and to slower tectonic changes. On shorter timescales, when temperatures rise and any existing ice on land melts, additional water flows into the oceans, raising global or eustatic sea level. When temperatures fall enough to allow more snow and ice to persist in high latitudes or on high plateaus, from year to year, more water is stored on land and sea level falls. In the mostly ice-free world of mature Pangea, these glaciostatic sea level changes are more modest than during times with large continental ice sheets, but they still influence the flooding and exposure of continental shelves and interior basins. On longer timescales, sea level is strongly affected by the rate at which new oceanic crust is produced at mid-ocean ridges, and by how much space exists in the ocean basins to hold water. When ridge systems are more active and stand higher, they displace water and raise average sea level, causing seas to transgress onto low-lying parts of the continents. When ridge activity slows and basins deepen, average sea level can fall and shallow epicontinental seas retreat. Because Pangea is surrounded by Panthalassa and bordered by the evolving Tethys region, these tectonically driven sea level changes periodically alter how much of the supercontinent's margins and interior basins are covered by shallow marine waters. Stratigraphic records from Pangean margins show repeated cycles in which marine sediments advance over coastal plains and then give way to river lake or desert deposits as sea level rises and falls. These transgressions and regressions do not tear the continent apart, but adjust the extent of shallow seas that fringe and intrude into it. In cooler episodes, early in the Pangea history, when remnants of Gondwanan ice still persist in high southern latitudes, sea level stands lower and more continental shelf is exposed. As the climate warms and ice melts, sea level rises, flooding coastal lowlands and creating broad, shallow seas in some areas. Later, as the supercontinent evolves and as mid-ocean ridge systems change height, sea level can reach high stands in which interior seaways spread widely across some parts of Pangea, connecting different coasts and influencing regional climates by bringing marine conditions inland. The extent and depth of such seas vary through time, and there is uncertainty in their exact outlines for particular intervals, because the rock record is incomplete and has been modified by later tectonic events. However, the overall pattern of multiple marine incursions and withdrawals is well established. In terms of ice, the mature Pangea interval is characterized by scarcity rather than abundance. Outside of polar oceans and high mountains, the land surface largely lacks permanent ice cover. High-latitude land areas can still experience snow in winter, and snow can persist for part of the year. But the conditions needed to maintain thick, long-lived ice sheets at sea level are not met under elevated greenhouse gas levels and warm mean temperatures. In high mountain ranges, formed along the collision zones at the heart of Pangea, or along its active margins, colder temperatures at altitude allow small glaciers to form in some intervals. These mountain glaciers and snowfields wax and wane with orbital cycles and with longer-term temperature changes, leaving behind glacial deposits and landforms in localized areas. Their influence on global sea level is limited because their total water volume is small compared with the volume of the oceans. Nonetheless, they provide evidence that even in a greenhouse world, local cold environments exist where altitude and latitude combine to lower temperatures, enough for ice to persist seasonally or over longer spans. There is uncertainty regarding the exact extent and longevity of such small ice bodies during different parts of the Pangea interval, because direct evidence is fragmentary and often overprinted by later erosion and tectonics. Overall, though the absence of widespread glacial deposits in most Pangean strata, combined with geochemical indicators of warm high-latitude conditions, supports the view that ice plays a secondary role in the climate system at this time. In a mostly ice-free world, the primary controls on temperature and sea level are greenhouse gas concentrations, tectonic reshaping of ocean basins, and the slow motions of the supercontinent that shift land and sea across climate zones. When these factors align to produce relatively cooler phases, sea level tends to fall modestly, snow and small glaciers expand in favored locations, and temperature gradients between equator and poles steepen slightly. When they shift toward warmer phases, sea level tends to rise, seasonal snowpacks shrink, small glaciers retreat, and polar regions warm, further flattening the gradients. Through all of these swings, Pangea remains a large, nearly continuous landmass on one side of the planet, and Earth's climate during its lifetime remains centered on a greenhouse state with only limited and localized ice. Across the surface of Pangea, water that falls as rain or snow does not simply vanish into the ground. It gathers into channels, ponds, and depressions, and moves along paths set by the shape of the land and by the balance between precipitation and evaporation. Because the supercontinent spans many latitudes and includes both wet coastal belts and dry interiors, its surface water systems range from large permanent rivers that flow to the sea to intermittent streams that lose themselves in inland basins where evaporation dominates. On the low-lying coastal margins that receive abundant rainfall from monsoon systems and from moist onshore winds, river networks are dense and active. In these regions, rainfall is frequent enough and soils are wet enough that hill slopes shed water into small tributaries that join to form larger channels. These rivers carry suspended sediment and dissolved ions from the weathering of rocks inland to the oceans and to marginal seas, such as the Tethys. Along the eastern and southeastern margins of Pangea, in some reconstructions where monsoon rains strike the coastal ranges and lowlands' broad river systems drain inland highlands and deliver water and sediment to the shoreline. As these rivers approach the sea, their gradients decrease, and they spread into deltas and coastal plains built of sand, silt, and mud. In these regions, shifting channels, floodplains, and marshes occupy wide belts parallel to the coast, and repeated flooding during wet seasons lays down layered deposits that record the pulse of the climate. In contrast, along more arid coasts, where cold upwelling currents keep sea surface temperatures low and reduce evaporation and rainfall, rivers are fewer and more seasonal. Streams may flow vigorously. Only during rare storms or during the short wet part of the year, then shrink or dry up, leaving behind dry channels that mark the routes of past flows. Sedimentary deposits from these margins often show coarse, gravel-rich layers laid down by brief energetic floods, separated by longer intervals of soil formation or aeolian reworking under dry conditions. Inland from the coasts, the structure of river systems reflects the strong contrasts in rainfall set by monsoon belts, trade winds, and rain shadows. On the windward sides of the central Pangean mountains and other major ranges, heavy rains feed large rivers that cut through foothills and carry water toward lower ground. Where these rivers can maintain continuous paths to the sea, they form through flowing systems that link interior regions to the margins, transporting not only water and sediment, but also dissolved nutrients and carbon from the land surface into the ocean. Where mountain belts intercept most of the moist air from the sea, however, the leeward sides receive far less rainfall. Here, rivers that begin on the flanks of the highlands or in rare upland catchments often lose volume as they move away from the mountains. In some cases, they are absorbed into the ground, feeding groundwater systems that discharge elsewhere or simply contributing to soil moisture. In other cases, they flow into low-lying interior basins that have no outlet to the sea. These endorheic basins, where drainage is inward rather than outward, are a distinctive feature of Pangea's dry interior. In such basins, water collects in lakes or wetlands when rainfall is sufficient, or when upstream rivers flow strongly. Because evaporation rates are high and inflow is limited and intermittent, These lakes often fluctuate in size and depth through seasons and longer climate cycles. During wet intervals, they can expand into broad, shallow bodies of water that receive fine sediment and dissolved salts. During dry intervals, they shrink or dry out completely, leaving behind mud flats and evaporate crusts. Over long periods, repeated cycles of flooding and desiccation build thick sequences of layered sediment composed of lake muds, evaporites such as salt and gypsum, and wind-blown dust. The presence of such sedimentary successions in the rock record of regions that once lay in the interior of Pangea provides strong evidence for widespread closed basins and variable lakes. Some interior basins are structurally controlled by tectonics, where the crust has been stretched and faulted during the early stages of rifting. Long, narrow depressions form. If these rift basins lie in climates that provide sufficient rainfall, they can host elongated lakes that parallel the faults. These lakes may be relatively deep and narrow with steep sides and limited shallow margins. They can persist for long intervals if the balance between inflow and evaporation remains roughly stable, and they can capture significant thicknesses of lake sediments. In more arid settings, similar fault-controlled basins may be occupied only briefly, by water acting instead as sites for dust accumulation and evaporate deposition. The distribution of lakes and drainage basins on Pangea therefore depends both on climate and on crustal structure. An important component of the surface water system on Pangea is groundwater, the water that infiltrates into the subsurface and moves slowly through pores and fractures in rocks and sediments. In wet regions, some fraction of rainfall and river water seeps downward, replenishing aquifers. These subterranean reservoirs can feed springs and base flow to rivers even during dry periods, smoothing out variations in surface flow. In dry interiors, groundwater recharge is more limited, but rare floods can still penetrate the subsurface along fractures and in coarse sediments, forming local aquifers that sustain small oases or wetlands. The presence of carbonate rocks and other soluble lithologies in some Pangean regions allows the development of karst systems, where groundwater dissolves rock and creates caves, sinkholes, and underground streams. In terms of regional patterns, the surface water network of Pangea can be envisioned as several major drainages radiating from highlands and plateaus toward the coasts, feeding large river systems where rainfall is sufficient, and as scattered, often disconnected drainage systems in the interior, many of which terminate in closed basins. The largest river systems likely occupy low-latitude and mid-latitude belts, where monsoon rains or consistent trade wind moisture supply feed long-lived streams. These could be comparable in scale to modern large rivers draining areas of several million square kilometers. Their lower courses host wide floodplains, meandering channels, and extensive wetlands. Farther poleward in cooler, but still largely ice-free climates, rivers draining temperate forests and open lowlands flow more steadily, with less extreme seasonal swings in discharge than their tropical counterparts, but still respond to variations in precipitation driven by mid-latitude storms and frontal systems. Evidence for these varied systems comes from fluvial sandstones, mudstones, with characteristic floodplain features, and fossil soils that form in riverine settings. In the desert belts and semi-arid regions of Pangea's interior surface, water is much more intermittent. Here, rainfall occurs infrequently, often in the form of intense but short-lived storms. These storms generate flash floods in ephemeral channels, carving gullies and transporting coarse sediment. When the floods spread out onto flatter ground at the foot of uplands, water loses velocity and drops its sediment load, forming alluvial fans and sheet flood deposits. Between storms, the channels may remain dry for long periods, and the land surface is shaped more by wind and slow creep than by flowing water. Soils in these regions are thin and often rich in soluble salts that accumulate because there is little leaching. Over time, the limited action of surface water here contrasts strongly with the more continuous fluvial shaping of wetter parts of the continent. On shorter timescales, seasonal changes in river flow and lake levels are governed by the timing of rainfall and snowmelt. In monsoon-influenced regions, rivers swell during the wet season when heavy rains fall over their headwaters and floodplains. They may overflow their banks, spread across adjacent lowlands, and then recede, leaving behind fresh layers of sediment and renewed soil moisture. During the dry season, flows diminish, channels may contract to a narrower path, and some side channels and oxbow lakes become isolated and stagnant. In higher latitude or higher elevation regions where winter precipitation falls, as snow spring and early summer snowmelt, can generate a predictable pulse of higher river discharge, followed by lower flows later in the year. Lakes in these regions can also show seasonal level changes, rising during melt and wet seasons and dropping during dry periods. Over longer intervals, as climate swings shift the balance between wetter and drier conditions, and as tectonic forces gradually change the elevation and tilt of the land, the pathways of rivers can be altered. Uplift of mountain ranges or plateaus can divert drainage from one basin to another. Subsidence of crust in other areas can create new space for lakes or shallow seas. River capture, where the headwaters of one river system are diverted into another by erosion and topographic change, can reorganize drainage patterns over large areas. In the context of Pangea, these processes operate over millions of years, while the overall form of the supercontinent remains intact, gradually adjusting the details of how surface water moves across its face. The combined effect of all these surface water processes is to link the atmosphere, land surface, and oceans in a continuous circulation of water. Rain falls on Pangea's mountains, and plains gathers into rivers or sinks into the ground, fills lakes and wetlands where basins allow, and ultimately either evaporates back into the atmosphere or returns to the sea. The exact routes and residence times differ from region to region, but everywhere the presence or absence of surface water and its movement or stillness is a product of the same factors: how much moisture the atmosphere delivers, how the land is shaped, how quickly water is lost to evaporation and infiltration, and whether there is a path from each point on the surface to the global ocean. During the lifetime of Pangea, this balance produces coastward river systems, interior endorheic basins, seasonal streams, and varied lakes that together define the hydrological character of the supercontinent's land surface. On the land surface of Pangea, the pattern of deserts, dune fields, and soils emerges directly from the distribution of rainfall and from the balance between moisture supply and evaporation described earlier. Where the atmosphere delivers frequent rain and humidity, is high soils can form that are thick, chemically altered, and rich in iron oxides and clays. Where rainfall is sparse and evaporation dominates bare rock, thin stony mantles and loose sand or dust are common, and desert landscapes expand. The supercontinent size ensures that broad belts of aridity develop in its interior, especially in subtropical to mid-latitude zones, beneath descending branches of atmospheric circulation cells and in the rain shadows cast by long mountain ranges. In these regions, low annual precipitation, high potential evaporation, and strong seasonal temperature contrasts together produce climates in which plant cover is sparse, surface runoff is limited, and wind plays a major role in shaping the landscape. Geological evidence and climate models both support the presence of extensive desert belts across central parts of Pangea, forming a rough band that stretches from what will later be parts of western North America and interior North Africa through regions that will correspond to the Middle East and Central Asia. In this band, sedimentary rocks interpreted as ancient desert deposits, including large-scale cross-bedded sandstones formed by migrating dunes, occur widely in the Permian and Triassic stratigraphic record. These rocks preserve the internal structure of dune fields that once covered large areas with ridges and mounds of sand tens of meters high, aligned with prevailing winds. The size and arrangement of the crossbeds indicate that winds were persistent in direction over long periods and that sediment supply was ample conditions consistent with arid interiors, far from stabilizing moisture. At the margins of these desert belts, conditions are somewhat less extreme. Here mean annual rainfall is still low, but occasional storms provide enough water to support discontinuous vegetation and to allow limited soil development. These semi-arid regions may host ephemeral streams that flow only after rain and alluvial fans that spread coarse sediment from uplands into lowlands. Soils in such areas tend to be thin and show features such as accumulations of calcium carbonate gypsum or other soluble salts in subsurface horizons, reflecting repeated cycles in which small amounts of water infiltrate the ground and then evaporate, leaving minerals behind. Over time, these processes create hardened layers, sometimes called calcretes or other duracrusts, that further influence water infiltration and root penetration. The presence of such soil features in ancient paleosols from Pangean strata indicates that large areas experienced prolonged semi-arid to arid conditions. In the cores of the deserts where rainfall is extremely scarce and surface water is almost absent, soils in the usual sense are poorly developed. Mechanical weathering such as thermal expansion and contraction and salt crystal growth breaks down rock into gravel and sand, while chemical weathering proceeds slowly because of the lack of water. Fine particles produced in these environments are easily lifted by wind and carried away, leaving behind coarse lag deposits or exposing bedrock. Wind erosion can create deflation surfaces where the ground surface has been lowered by the removal of loose material and can sculpt ventifax stones that bear faceted surfaces from abrasion by wind-driven grains. In closed basins within these deserts, occasional inflows of water from distant storms can form shallow playas that dry out quickly. Each cycle of wetting and drying concentrates dissolved salts, leading to crusts and beds of evaporites. These features are recorded in the rock record as sequences of thinly laminated mudstones and evaporate layers, showing that deserts were not static, but experienced episodic water input and intense evaporation. The dune fields of Pangea's interior are particularly significant in illustrating how wind reshapes the dry landscape. Under conditions of steady wind and abundant loose sand, dunes can migrate across the surface, moving downwind as sand grains are picked up on the windward side and avalanche down the slip face. In plan view, dune systems can form linear transverse or star-like patterns depending on wind variability. In cross-section, they are preserved as large inclined layers that dip in the direction of dune migration. Many Permian and Triassic sandstones deposited within the interior of Pangea show such structures on scales of several meters to tens of meters, indicating extensive, long-lived erg systems or sand seas. The orientation of the crossbeds provides information about the prevailing wind directions at the time and supports the inference of strong atmospheric circulation features over the supercontinent's dry belts. Beyond the ergs, wind also transports finer particles as dust, forming blankets of loess. When this dust settles and accumulates in transition zones between deserts and more humid regions or downwind of large dry basins, layers of fine silt with characteristic massive or weakly layered structure, often interpreted as wind-blown deposits, are preserved. These loess-like sediments can mantle older landforms and provide parent material for soils in regions that receive somewhat more rainfall, illustrating the link between arid source areas and more distant, slightly wetter landscapes. Where moisture is more abundant, even within a generally warm climate, soils develop more fully. In low-latitude regions of Pangea that are under the influence of persistent warmth and seasonally high rainfall, chemical weathering of rocks proceeds rapidly. Feldspar and other primary minerals break down to form clays and oxides, and soluble components are leached downward or removed entirely by drainage. The resulting deep iron-rich soils can have bright reddish or reddish-brown colors due to iron oxide coatings on mineral grains. Such soils, often called lateritic or strongly weathered tropical soils, in modern analogs, reflect long periods of intense weathering under conditions where input of material from outside is limited and removal of soluble components is efficient. Their presence in the rock record of Pangea's low-latitude belts is inferred from thick profiles of altered rock and from geochemical signatures that show strong depletion of mobile elements relative to resistant ones. In more temperate regions, soils may be moderately leached and show a clearer layering of horizons, with organic-rich upper layers grading down into zones of clay accumulation and then into less altered parent material. Although organic matter content is ultimately controlled by vegetation, which is discussed more fully later, the physical and chemical processes of soil formation depend on climate parent rock and time. In regions where moderate rainfall and seasonal temperatures prevail, the rate of chemical weathering is slower than in tropical belts, but faster than in deserts, leading to intermediate soil types that still participate actively in the cycling of nutrients and in controlling runoff and infiltration patterns. In areas that experience strong wet and dry seasons, as in some monsoon-influenced belts on Pangea soils, can display features related to repeated shrink-swell cycles. Clays that expand when wet and contract when dry can form cracks that open and close with the seasons. These cracks may fill with sediments or organic material when open and leave distinctive patterns in the soil profile when preserved. The alternation of red or brown oxidized zones with more reduced grayish or mottled zones can reflect fluctuating water tables and variable oxygen availability in the soil, again tied to the seasonal rhythm of rainfall. Such features documented in ancient paleosols help reconstruct the seasonal climate regimes that affected different parts of the supercontinent. The arrangement of deserts and soil types on Pangea thus follows broad latitudinal and continentality-controlled belts modified locally by topography and hydrology. Near the coasts and in regions where moisture from Panthalassa and the Tethys region can penetrate soils, are thicker and more chemically evolved supporting landscapes, where weathering has significantly altered the underlying rocks. Inland behind mountain barriers and under subsiding branches of atmospheric circulation soils, thin and desert surfaces dominate with extensive ergs, deflation plains, salt flats, and rocky uplands. Between these extremes, transitional zones host semi-arid soils, with accumulations of carbonates and other salts, as well as loess mantles downwind of dry source areas. Over millions of years, the movement of the continents and slow shifts in climate cause these belts to migrate. But during the main Pangea interval, the overall pattern remains one of strong contrast between humid, deeply weathered margins and vast arid interiors. These patterns influence not only the physical appearance of the land surface, but also the way in which water infiltrates or runs off, the rate at which rocks, weather, and nutrients are released, and the kinds of substrates available for plants when they occupy these regions. The record of ancient dunes, evaporates, paleosols, and weathering profiles preserved in the strata of former Pangean terrains provides a direct window into this distribution of deserts and soils, and together with climate modeling supports a coherent picture of a supercontinent whose land surface is divided into sharply differentiated zones of dryness and wetness, with corresponding differences in the ground beneath. On the land surface of Pangea, living communities of plants and animals arrange themselves in patterns that follow the gradients of moisture, temperature, and soil described earlier. Because the global climate during much of the Pangea interval is warm and largely free of extensive low-latitude ice, temperature is less often the main limit on where land life can persist. Instead, the key control is water. Where air and soils are wet for large parts of the year, dense forests form. Where water is present only seasonally or in moderate amounts, more open woodlands and savannas dominate. Where moisture is scarce and evaporation is strong, vegetation is sparse and desert-adapted communities occupy the landscape. Fossils of plants, wood spores, and pollen, together with the remains and tracks of land animals and the characteristics of ancient soils, record these patterns and show how they change as climate and geography evolve during the life of Pangea. Along low-latitude coastal belts that receive abundant rainfall from monsoon systems and moist onshore winds, forests are widespread. In the late Paleozoic, before and during the early stages of Pangea's assembly, some of these forests include dense stands of seed ferns and other plants adapted to humid conditions, especially in what will become parts of Gondwana. As the climate warms into a greenhouse state, and as the distribution of rainfall shifts, these older humid floras give way to communities dominated by gymnosperms such as coniferous cycads and ginkgo relatives, along with ferns and horsetails in wetter microsites. In the Triassic and early Jurassic portions of the Pangea interval, many lowland and mid-elevation regions that remain relatively wet host coniferous and mixed forests, in which tall trees form a canopy and shrubs, ferns, and ground cover plants occupy the understory. Coal deposits formed from the accumulation and burial of plant material in waterlogged settings testify to the persistence of swampy forests and wetlands in some coastal and near-coastal zones, particularly in areas where high rainfall and slow drainage coincide. The species composition of these forests differs from modern tropical rainforests, but the structural role of dense tree cover and persistent moisture is similar in ecological terms. Where the seasonal cycle of rainfall is strong as in monsoon-influenced belts on the flanks of Pangea forests, adjust to a rhythm of wet and dry periods. In such regions, trees and other plants must cope with months of heavy rain followed by months of reduced rainfall. Fossil evidence indicates that some forest types in these belts are deciduous, shedding leaves during the dry season to reduce water loss and regrowing them when rains return. The soils beneath these forests show signs of repeated wetting and drying, and the preserved plant assemblages shift through the stratigraphic record in ways that reflect changes in the strength and length of wet seasons. In areas where annual rainfall is high enough and the dry season is short-closed, canopy forests continue to dominate. Where the dry season is longer or more intense, forests give way to more open woodlands with grassy or shrubby understories. In these transitional zones, often described as savannas, in a broad sense, tree cover is discontinuous. Individual trees or clumps of trees are spaced apart, and herbaceous plants occupy the spaces between. The fossil record of grasses as a group is sparse and late compared with the Pangea interval. So these ancient savannas are not grass-dominated in the modern sense, but they still represent environments where tree density is limited by water availability, and where seasonal changes in moisture strongly influence plant growth and leaf cover. Vertebrate fossils from such settings include a mix of forms adapted for browsing on shrubs and low tree branches, and forms that may have grazed more on low vegetation, reflecting the mosaic of plant life present. Moving farther into the interior of Pangea, where overall rainfall decreases and deserts and semi-deserts become extensive, plant life becomes more sparse and more strongly adapted to drought. In these arid belts, vegetation may be confined to river corridors, lake margins, and rare oases where groundwater reaches the surface. Away from these refuges, the landscape is dominated by bare rock gravel dunes and thin soils. Fossil plant assemblages in these areas are often poor in diversity and abundance, limited to drought-tolerant shrubs. Small trees in protected hollows and ephemeral plants that complete their life cycles quickly after rare rains. Soil profiles show accumulations of soluble salts and carbonate nodules rather than thick, humus-rich layers. Trace fossils of roots may be present, but are spaced widely, indicating low plant density. Animal life in these desert interiors is likewise adapted to scarce water and strong temperature contrasts. Tracks and bone beds record the presence of reptiles, including early archosaurs and their relatives, and of synapsids and other tetrapods that can tolerate arid conditions. The distribution of these fossils suggests that many animals concentrate along water courses and near lakes, moving across open desert surfaces primarily when conditions allow. Despite the harshness of these environments, they are a persistent and important part of Pangea's ecological map. At higher latitudes on Pangea, where temperatures are cooler but still not dominated by large ice sheets, land ecosystems reflect the combination of milder summers, colder winters, and varying day length. Fossil floras from these regions include conifer-dominated forests with understories of ferns and other spore-bearing plants. In some intervals, deciduous trees adapted to strong seasonal light cycles appear. The presence of tree rings in fossil wood with clear patterns of seasonal growth and dormancy indicates that plant communities in these latitudes respond to marked annual cycles in temperature and light, even in a greenhouse climate. In coastal high-latitude zones where warm currents moderate temperatures and where moisture from the sea is available, forests may extend close to the polar circles, forming continuous belts of vegetation that experience long summer days and long winter nights, but relatively mild conditions compared with icehouse periods. Inland at similar latitudes where continentality is stronger and precipitation lower, more open woodlands and steppe-like communities prevail, forming another set of transitional biomes in the Pangean mosaic. Elevation adds a vertical dimension to these patterns. Mountain ranges within Pangea, especially the long belts formed at the collision zones between the northern and southern parts of the supercontinent, host altitudinal zonation in vegetation. Lower slopes may support the same forest types as adjacent lowlands, while higher elevations experience cooler temperatures, more frequent cloud cover, and in some intervals, greater snowfall. Fossil soils and plant remains suggest that highland regions can support communities more similar to those at higher latitudes with coniferous forests, giving way to more open shrub-dominated or tundra-like vegetation near the highest elevations. Small glaciers and persistent snowfields in some mountain belts where conditions create additional local moisture sources and support cold-tolerant plant and animal communities that are absent from the surrounding lowlands. Over time, as these ranges rise and erode, the vertical distributions of biomes shift. Through the Pangea interval, life on land also responds to several major disruptions tied to changes in climate and to events that alter ocean chemistry and atmospheric composition. The end Permian mass extinction, which occurs when Pangea is already assembled, removes a large fraction of marine species and significantly affects terrestrial communities. Plant fossil records across this boundary show a turnover from older swamp and Glossopteris-dominated floras in parts of Gondwana to more drought-tolerant gymnosperm-dominated floras in the Triassic. Coal formation declines sharply in many regions, consistent with the loss of extensive peat-forming wetlands and the spread of more open, seasonally dry habitats. On land, many synapsid lineages decline or disappear, and new groups of reptiles and early dinosaurs expand into ecological roles in the Triassic landscapes. These changes are not uniform across all of Pangea, but occur against the backdrop of the moisture and temperature gradients already described, so that forest belts, savannas, and deserts reorganize in both composition and geography. Later, around the Triassic to Jurassic boundary, another significant extinction affects marine and terrestrial life, altering the composition of land faunas once more and marking the rise of dinosaurs as more dominant terrestrial vertebrates in the Jurassic. Again, plant communities adjust with gymnosperm-dominated forests persisting in many regions, but with gradual shifts in species composition and in the relative abundance of different growth forms. Throughout these intervals, the structure of Pangea and its climate continue to shape where different biomes can exist. Coastal wet belts remain centers of forest growth and recovery after disturbances, while interior arid zones remain more sparsely vegetated and more sensitive to shifts in rainfall. The fossil record shows that despite repeated disruptions, forests reestablish in suitable climates, savannas, and open woodlands continue, where seasonal water limits tree density and desert ecosystems persist in the driest belts. The distribution of life across Pangea thus reflects a dynamic interplay between climate, soils, topography, and evolutionary change. Forests occupy humid lowlands and montane zones where water is plentiful and temperatures support year-round or seasonal growth. Savannas and open woodlands span the transition from these wet belts to the drier interior, where water is sufficient for trees only in patches and seasons. Deserts and semi-deserts fill the arid cores and rain shadows where moisture is scant and plants and animals adapt to long periods without rain. High latitude and high elevation regions host their own variants of these patterns, modified by cooler temperatures and strong seasonal cycles in light. All of these biomes change in composition through the Pangea interval as extinction events and ongoing evolution reshape the identities of the species present. But the underlying arrangement of habitats follows the physical gradients set by the supercontinent's climate and land surface. Around the edges of Pangea, the contact between land and sea is not a single uniform line, but a complex belt of coastal shelves, embayments, interior seaways, and deeper slopes. In these shallow and intermediate depth, water's marine life forms distinct zones that respond to temperature, salinity, light oxygen, and nutrient supply, all of which are shaped by the circulation patterns and basin geometries already in place during the Pangea interval. The broad Panthalassa Ocean provides open ocean environments, while the more segmented Tethys region and various epicontinental seas along the margins of the supercontinent create settings where coastal and shallow marine ecosystems can flourish, change, and sometimes collapse. Continental shelves around Pangea are the primary sites where shallow seas develop. These shelves are areas of relatively low water depth extending outward from the coasts before the seafloor drops off along the continental slope. Their width varies from place to place depending on crustal structure and sea level. In times of higher sea level, more of the shelf is flooded, creating broad, shallow seas. In times of lower sea level, shorelines shift seaward, exposing more of the shelf as coastal plains. In both cases, the general pattern is that near-shore waters are shallower, more influenced by sediment and freshwater input, and more variable, while outer shelf regions are somewhat deeper, clearer, and more stable in temperature and salinity. Along low-latitude coasts, where warm currents from Panthalassa or from the Tethys region flow, sea surface temperatures remain high through much of the year. Here, shallow, sunlit waters provide conditions favorable for carbonate-producing organisms, including various reef-building and sediment-producing groups. During different parts of the Pangea interval, these groups change. In the late Paleozoic, before the full development of Triassic reef systems, carbonate platforms may be built by combinations of sponges, calcareous algae, and other invertebrates. After the end, Permian extinction reef ecosystems collapse in many places, and for a time early in the Triassic, large complex reefs are scarce. As recovery progresses, new reef-building communities arise, including associations of scleractinian corals and other organisms that construct walls and frameworks capable of withstanding wave energy along shelf edges. In the early to middle Mesozoic portion of the Pangea interval, these reefs occupy belts of shallow, clear, warm water commonly along the margins of the Tethys region and in low-latitude parts of Panthalassa's continental shelves. Within these reef belts, marine life is diverse. The reef framework itself provides hard substrate and complex three-dimensional structure. Corals, sponges, bryozoans, and other encrusting and branching organisms attach to surfaces. Between them, spaces fill with sediments and with smaller organisms. Algae grow on exposed surfaces and contribute to carbonate production. In the water above and around the reefs, plankton, small invertebrates, and fish feed on suspended particles and on each other, forming food webs tied closely to the reef structure. On the seaward side, the reef crest absorbs wave energy, while on the landward side, quieter lagoonal environments develop with finer sediment seagrass-like plant communities where such plants exist, and a different suite of organisms adapted to calmer, sometimes more variable conditions. The exact composition of reef communities changes through time and from basin to basin, but the overall pattern of zoned habitats, from shoreward lagoons across reef flats to outer slopes, is a consistent feature of shallow, warm seas during much of the Pangea interval. Not all shelves are suitable for reef growth. Along coasts, where rivers deliver large volumes of fresh water and sediment, water can be more turbid and less saline. In such settings, silicic-clastic input dominates over carbonate production. Near river mouths, deltas and estuaries form with shifting channels and sandbars. Suspended sediment reduces light penetration, limiting the depth at which photosynthetic organisms can thrive. Salinity may fluctuate as tides and river discharge interact, creating stress for organisms sensitive to such changes. Nonetheless, these muddy and sandy nearshore environments support their own communities, including burrowing invertebrates, mollusks, and fishes, adapted to living in soft substrates. Plants that tolerate brackish water fill coastal marshes and wetlands, linking marine and terrestrial ecosystems. Sedimentary structures such as crossbedding, ripple marks, and trace fossils of burrows and tracks record the activity of these communities and the influence of tides and waves on the seafloor. Farther out on the shelf, where river influence is weaker and sediment is finer, settings resemble modern open shelves with relatively well-mixed water columns and more stable salinity. Here, carbonate producers can contribute more even if large reef frameworks are absent, and fine carbonate muds and bioclastic sands accumulate from the shells and skeletons of plankton and benthic organisms. The Tethys region adds further complexity to these coastal and shallow marine systems. Because Tethyan basins are partly enclosed and connected by sills and straits, water exchange with the open Panthalassa Ocean can be limited. In some Tethys sectors, high evaporation rates, warm temperatures, and restricted circulation lead to higher salinity at the surface. If this dense saline water sinks, it can drive internal overturning within the basin. If it remains at the surface, it can stress organisms that are less tolerant of salinity fluctuations. In the most restricted subbasins, especially where the balance of evaporation and inflow is extreme, salinity can reach levels high enough to cause widespread precipitation of salts such as gypsum and halite. Their shallow lagoons and sabkha's coastal flats, subject to periodic flooding and drying, alternate between being shallow brine pools and dry salt crusts. Organisms in these environments are limited to halo-tolerant microbes and a few invertebrates, while more typical marine ecosystems are confined to more open parts of the basin. At the same time, other parts of the tethys, especially those with better connection to the open ocean and a steady supply of nutrients from rivers and upwelling, support rich marine life in their shallow and deeper waters. The combination of warm temperatures, broad shelves, and varied basin geometry makes tethys a major center of marine biodiversity during parts of the Triassic and Jurassic. Open ocean environments of Panthalassa host their own vertical and horizontal zones. Near the surface, in the sunlit layer known as the photic zone, phytoplankton carry out photosynthesis, forming the base of the marine food web. These microscopic plants and plant-like organisms convert dissolved nutrients and carbon into organic matter, which supports populations of zooplankton and larger animals. In the warm greenhouse world of Pangea, nutrient distributions in surface waters are influenced by upwelling zones along eastern boundaries, by equatorial divergence, and by river input from the supercontinent's margins. In regions where upwelling brings nutrient-rich water to the surface, primary productivity can be high, supporting dense plankton communities and, in turn, abundant tectonic and pelagic predators, such as fish, cephalopods, and marine reptiles. In more stratified regions with fewer nutrients reaching the surface, productivity is lower and the water is clearer, but the basic structure of a plankton-based food web persists. Below the photic zone, light levels drop and life depends on organic matter produced above. Sinking particles of plankton remains fecal pellets, and larger carcasses carry carbon and nutrients downward, where they are consumed by bacteria and by animals adapted to low light and low temperature. The depth at which oxygen is lowest, often in an oxygen minimum zone, is set by the balance between the amount of sinking organic matter and the rate at which oxygen-rich water can be supplied from above or from high-latitude sources. In parts of Panthalassa and tethys, where productivity is high and ventilation-limited oxygen minimum zones can be pronounced, squeezing the habitable vertical space for some organisms. In extreme cases, especially during intervals of widespread oceanic anoxia, bottom waters over large regions can become oxygen-poor or anoxic, reducing the extent of habitable benthic environments and stressing marine communities. During the Pangea interval, the marine biosphere experiences several such episodes. The end, Permian extinction, is associated with major disruptions in ocean chemistry, including evidence for expanded anoxic conditions in both shallow and deep waters. Reef communities collapse, many marine invertebrate groups suffer heavy losses, and carbonate production on shelves declines. Recovery in the early Triassic is slow, with simple microbial communities dominating some platforms before more complex reef builders reappear. Later, at the Triassic to Jurassic boundary, another crisis affects marine life, with losses among ammonoids, some fish groups, and reef builders. Each of these disruptions reshapes the distribution and composition of coastal and shallow marine ecosystems against the fixed backdrop of Pangea's geography. Shallow shelves that once supported diverse reefs may become dominated by microbial carbonate structures or by non-reef carbonate producers. Regions that once hosted well-oxygenated benthic communities may experience hypoxia or anoxia until circulation and productivity patterns shift. Where oxygen remains adequate and other conditions are favorable, new reef systems and benthic communities eventually establish, building on the physical template of existing shelves, slopes, and basins. Along the continental slopes and in deeper marginal basins, marine communities adjust to gradients in light pressure and oxygen. Slope environments host organisms adapted to living on fine sediments under lower light, including infaunal invertebrates that burrow into the seafloor and epifaunal species that sit on its surface. In settings where oxygen consumption in deeper waters is high and replenishment slow, only tolerant species can survive at depth, and diversity declines with increasing distance from well-ventilated regions. In better ventilated parts of the margin, more diverse communities can exist down the slope and onto the rise. Throughout these zones, downslope transport of sediment from the shelf via gravity flows and turbidity currents can periodically disturb the seafloor, burying organisms and shaping the distribution of habitats. Marine vertebrates during the Pangea interval occupy a range of environments from coastal shallows to the open ocean. Early reptiles adapted to marine life, such as ichthyosaurs and sauropterygians in the Triassic and Jurassic exploit niches as large predators in shelf seas and in offshore waters. Their distribution is influenced by the arrangement of basins and by the availability of prey. Fish and cephalopods likewise respond to productivity patterns and to migratory pathways set by currents. The presence of narrow seaways and interior basins in the Tethys region can create partial barriers and corridors for dispersal, leading to differences in faunal composition between basins, even where physical conditions are similar. Over the entire lifetime of Pangea coastal seas, reefs and marine life zones thus follow a pattern controlled by basin geometry, circulation, and climate. Warm, shallow shelves in low latitudes, particularly along the Tethys and some panthalassan margins, host carbonate platforms and reefs when water is clear and nutrients moderate. River-influenced shelves near large drainage outlets host silica-clastic-dominated environments with deltas, estuaries, and mud-rich plains. Semi-enclosed basins with restricted exchange can develop elevated salinity and low oxygen, leading to evaporate deposition and anoxic bottom waters, while better connected shelves and slopes maintain more typical ventilated marine conditions. Open ocean waters support plankton-based food webs structured by upwelling and stratification, and the vertical arrangement of life reflects the distribution of light and oxygen. Episodes of environmental stress, particularly those tied to carbon cycle disturbances and anoxia, reorganize these systems at intervals. But the underlying division into coastal shelf slope and open ocean zones persists, while Pangea exists as a supercontinent surrounded and penetrated by seas. The existence of Pangea as a single broad landmass is the surface expression of deeper processes within Earth, where rigid plates of lithosphere move slowly over a weaker, convecting mantle. The lithosphere is the outer shell of rock made of crust and the uppermost mantle that behaves as a strong layer on geological time scales. Beneath it, in the upper mantle, temperatures and pressures allow rocks to deform more readily, so that this region, sometimes called the asthenosphere, can flow very slowly. Heat escapes from Earth's interior by convection in this mantle layer, and the moving mantle drags and interacts with the overlying plates, causing them to diverge, converge, and slide past one another. Pangea forms when several earlier continents converge into one, which means that over tens of millions of years before and during its assembly, oceanic lithosphere between these continents sinks into the mantle along subduction zones. As this process continues, oceans that once lay between the continents become narrower. The leading edges of the continents move toward one another, and the trenches where subduction occurs migrate as the slabs of oceanic crust sink. Eventually, the last strips of oceanic crust between approaching continents are consumed, and the buoyant continental crusts collide. Because continental crust is relatively light and thick, it resists sinking into the mantle. Instead, the colliding continents crumple and thicken, producing long mountain belts and deep crustal roots. The central Pangean mountains, which later leave behind parts of the Appalachian system in eastern North America, the Variscan and related belts in Europe, and ranges in northwestern Africa, are the record of such collisions. In these zones, rocks from former continental margins, ocean floor, and island arcs are stacked, folded, and metamorphosed. Granitic magmas generated by melting within the thickened crust rise and solidify, adding new bodies of intrusive rock. At the surface, the mountain belt stands as a long highland that marks the suture where earlier oceans have closed. To the north and east, further collisions close additional seaways and build the Ural Mountains between what will become Eastern Europe and Western Siberia, extending the network of orogenic belts that knit the northern lobe of Pangea together. Along the southern margin of Gondwana, repeated episodes of subduction and collision build yet more long belts of deformed rock. These collisions and mountain-building events represent the final stages of a long cycle in which plates have drifted, oceans have opened, and then those oceans have closed again. Once Pangea has assembled, convergence and subduction do not cease. Around much of the outer margin of Panthalassa, oceanic plates continue to sink beneath the edges of the supercontinent or beneath island arcs and microcontinents. These long arcs of subduction form chains of volcanoes and generate magmatic activity that builds and modifies the margins of Pangea. Where oceanic lithosphere descends beneath continental lithosphere, the downgoing plate releases water into the overlying mantle wedge, lowering its melting point and generating magmas that rise to feed arc volcanoes. These volcanic arcs contribute new igneous rocks to the edges of the continents and build volcanic mountain ranges parallel to the trench. Sediments scraped from the descending slab accumulate in accretionary wedges, thick piles of deformed material at the edge of the continent. Together, arc magmatism and accretion add mass to Pangea's margins, over time subtly altering their shape and thickness. At the same time, the sinking slabs of oceanic lithosphere help drive plate motions by pulling plates towards subduction zones, a process often referred to as slab pull. In the interior of the supercontinent, far from these active edges, the lithosphere is relatively thick and stable, forming cratons and shields that host ancient rocks. These stable cores underlie large parts of Gondwana and Laurasia and help support the weight of the overlying mountains and plateaus. However, even within the interior, the lithosphere is not entirely passive. Heat from the mantle accumulates beneath the insulating mass of Pangea, and variations in mantle flow can lead to regions of uplift or extension. In some models, mantle convection during the time of Pangea features large-scale upwellings beneath or near the supercontinent, sometimes described as superplumes, though the exact configuration and persistence of such structures are still topics of study and debate. What is clear is that where mantle flow tends upward and where lithospheric stresses allow the continental crust can be stretched and thinned, setting the stage for rifting. Rifting is the process by which a continental plate is pulled apart. As extension begins, normal faults form, and the crust breaks into blocks that tilt and drop down, creating rift basins. These basins are often filled with sediments eroded from nearby uplifts and with volcanic rocks produced by decompression melting of the underlying mantle. In the late stages of Pangea's life, such rifts appear in what will become the central Atlantic region and in other parts of Gondwana. In the future eastern margin of North America, for example, early Mesozoic rift basins record subsidence and volcanism as the lithosphere is stretched. The same process occurs along the future margins of Africa, South America, and other fragments. Initially, these rifts are narrow and confined to continental crust, and Pangea remains intact as a single landmass. As extension continues, however, the lithosphere can thin to the point where mantle material rises closer to the surface, melts, and forms new oceanic crust. When this happens, a mid-ocean ridge develops within the former continental interior, and a new ocean basin begins to open. The earliest stages of this transition during the Pangea interval are marked by widespread emplacement of basaltic lava and intrusive rocks associated with large igneous provinces. The Central Atlantic Magmatic Province, for example, is a vast region of basaltic magmatism that erupts around the time when rifting between what will become North America, South America, Europe, and northwestern Africa intensifies. Lava flows, dikes, and sills spread across large areas, intruding and covering the existing continental crust. This magmatic pulse is linked to decompression, melting of mantle beneath the stretching lithosphere, and possibly to focused mantle upwelling at depth. Earlier in the Pangea story, another large igneous province, the Siberian Traps, erupts in what will become Siberia near the end of the Permian period. There, too, enormous volumes of basaltic lava and magmatic intrusions are emplaced over a geologically short interval. These magmatic events represent times when heat and material from deep within Earth reach the surface in exceptional amounts. The gases released by such eruptions, including carbon dioxide, sulfur species, and other volatiles, enter the atmosphere and oceans, affecting climate, ocean chemistry, and the biosphere. The end Permian and Triassic to Jurassic mass extinctions coincide in time with the Siberian Traps and Central Atlantic magmatism, respectively, suggesting that deep Earth processes can trigger or amplify surface environmental crises. The uncertainties lie in the precise causal chains and in the relative roles of different gas species and feedbacks, but the broad connection between large igneous provinces, carbon cycle disturbances, and biological change is supported by many lines of evidence. Over the full length of Pangea's existence, the long-term carbon cycle links these tectonic and magmatic processes to climate. Carbon dioxide enters the atmosphere primarily through volcanic degassing at mid-ocean ridges arcs and large igneous provinces, as well as through metamorphic decarbonation of rocks, pushed deep in orogenic belts. It is removed from the atmosphere over longer timescales by the weathering of silicate rocks on land and by the burial of carbon in sediments. When carbon dioxide dissolves in rainwater, it forms a weak acid. This slightly acidic water reacts with silicate minerals in rocks, breaking them down and releasing cations that are carried by rivers to the ocean. There, these ions combine with carbonate to form carbonate minerals that are deposited as sediment and eventually buried in the crust. This process effectively transfers carbon from the atmosphere to solid Earth reservoirs. The rate at which this happens depends on temperature, precipitation, and the availability of fresh rock surfaces. Uplift of mountain belts during Pangea's assembly exposes large areas of fractured, newly raised rock to weathering. In warm, wet regions along the margins and in monsoon belts, chemical weathering is intense, enhancing the drawdown of carbon dioxide. In contrast, arid interiors with little water see slower weathering. The balance between these regions, together with the global distribution of mountain belts and lowlands, influences how quickly the long-term carbon sink operates. At the same time, broad shallow shelves and interior seas created by sea level high stands provide places where carbon can be buried as carbonate sediments and organic rich muds. When conditions in the ocean favor widespread low oxygen environments, as during some intervals of Pangea's history, organic carbon burial can increase, further drawing down carbon dioxide. Thus, the tectonic setting of Pangea, with its long sutures, highlands, evolving shelves, and episodic magmatic outburst, shapes the climate through its control of the carbon cycle. Erosion of Pangea's mountain belts and highlands is continuous once uplift occurs. Rain rivers and glaciers, where they exist, remove material from the peaks and transport it to lower ground. Sediment loads carried by rivers form thick deposits in foreland basins that develop adjacent to the growing mountains, where the weight of the rising range and the load of sediment flex the lithosphere downward. These basins act as sinks for sand, silt, and mud, some of which later lithify into sedimentary rocks that preserve records of the environments present at the time. As erosion removes mass from the mountains, isostatic adjustment causes the crust to rise, partly compensating for the loss and prolonging the life of the highlands. Eventually, however, over very long time scales, even large mountain ranges are worn down and their material is redistributed across the continent and into the ocean. This continual reshaping of topography feeds back into climate by altering wind patterns, rain shadow positions, and drainage networks. Beneath all of this mantle convection continues to move heat from Earth's interior toward the surface. Cold slabs of oceanic lithosphere from Panthalassa sink into the mantle beneath subduction zones, carrying surface material deep underground and contributing to large-scale patterns of mantle flow. Warm mantle rises elsewhere, including beneath mid-ocean ridges that form as new oceans open during the breakup of Pangea. The positions of upwellings and downwellings help determine where continents are drawn together and where they are pulled apart. In one phase of the cycle, continents collect into a supercontinent, like Pangea, above convergent mantle flow. In a later phase, extended heating and insulation from the large landmass, and changing mantle patterns favor rifting and dispersal. While Pangea exists, it is thus one stage in a repeated sequence of assembly and breakup, driven by the thermal and mechanical behavior of the planet's interior. The rocks exposed in Pangea's mountains, basins, and margins, the pattern of plate motions, and the distribution of magmatic and metamorphic belts all reflect the operation of these deep drivers during the interval when most of Earth's continental crust is joined into a single supercontinent.